Today it's gonna be a very different video. Instead of like just building stuff, we're actually gonna have a call. This is gonna be a Zoom call with my friend Manit. Manit is an electrical engineer, and I'm not an electrical engineer. And hopefully he's gonna do a crash course on how we can create a power PCB. So on the previous video, we cleaned up all of the wiring. We've packaged the boards better on the robot, but we're still gonna have a lot of cables. There's just no way around it with that many boards we have, unless we consolidate all boards into a single power PCB. Now, I've never actually built a PCB, so I've asked him for help, and he's gonna show us how to do these, and he's gonna do it. Hopefully we can do the entire thing in one video. I don't know how long it takes to build one of these things, but we'll see. And yeah, let's get to it. Should we do an intro? Do you want to tell the world who you are?
Why don't you give me an intro?
All right. Okay, so this is Manit. He's a good friend. We met at Tesla. Then you went to work at NASA. And then you started your own, basically, engineering company. Now you're a CTO at a warehouse robotics company. Your background is in electrical engineering, right? You've also built rockets, like for your rocketry team in university. I think that covers it, right?
Yeah.
Did I miss anything? We built a few things in the past.
Right. We worked on a few side projects in the past. I think that was a great intro. Thanks. That's
yeah.
Now I feel like people are gonna have way too high of an expectation for me though. So.
Well, the other thing I was gonna say is yeah, okay. And for context, today, the topic is the power PCB, right? So on the last video I made, like I was, and I haven't shown you this, man, but I was changing the CAD to basically fix the wires on the robot because it currently looks like this. Like there's a bunch of spaghetti on top of it,
Yeah.
and so I cleaned it up a bunch, as much as I could. And actually, let me share my screen. But the real next step to really clean it up is to have a power PCB. And like I was saying earlier, it sounds hard. Like I can't believe I'm saying this, but I've never designed a PCB before. So I was hoping you would come in here and teach us. So this is the robot. Obviously, the Arduino board here. I put mounting holes for everything. I made holes to route all the wires. On the underside, we have a bus bar and a battery. I kind of hate how this looks. This was kind of like on the fly design. Obviously, the robot that starts looks very chunky. I do hate it. But what do you think? What's the design review?
It looks good. Where did you find that bottle of that buck converter? That's actually really interesting.
Yeah. So it turns out the I don't even know, the dingus guys.
Yes.
Basically, they use the same buck converter, and I think they modeled it.
Yeah. Okay, that's good. It's nice to know that. Well, it's probably about the same.
It's I measured to be the same. Yeah.
Yeah, we'll talk about that buck converter and generally how I think we can get smaller form factor, or at least the same form factor or the same size with more capabilities. There's quite a lot of interesting stuff that happens with power supply design for this, but I think we should be able to fit everything that we want in that same space, if not slightly bigger, but it looks like we definitely have enough space there.
Everything power wise, right?
Yeah,
Dude, by the way, I was about to take off these heat sinks because
you probably can.
yeah, it's just a screw, and like look at these fins here.
Way too large for what that thing is.
Yeah, and I feel like they're meant for some airflow, which we don't have here anyways. So
Yeah, you don't need that much heat sinking, honestly. I mean, the only reason they have them there is likely because that board is only 2 layers and only like 1 or ½ ounce copper in the actual PCB, so you're not getting a lot of heat sinking through the PCB itself. So
interesting.
they're probably slapping on. What I find funny though is that nothing is really, and you can't really do heat sinking on an inductor, but the inductor is one of the things that will warm up the most in about.
So this guy here, the ring.
Yeah, the big ring. Yeah. And I'll show you some cool like test data that some of the companies have put out on like some of their reference designs. designs, and that's something I wanted to show you because really, when it comes to practical design of these things, you kind of want to just copy somebody else's design, especially if their entire purpose is to sell you the chips that you want to use on that design. So we'll kind of go through that, but it's kind of, I also saw those heat sinks and I was like, I don't know why they have such large heat sinks, because even at 300 watts, you're not going to need that much area to...
By the way, these are MOSFETs, right?
Yes.
Okay. Wouldn't those be the ones getting super warm?
Those will also get warm.
Okay, yeah.
The three main things that will get warm are the switches. So there's two switches, one on each side, and then the inductor, and anything that is close by to those things.
Which ones would be the switches here? You can't tell, right? They're on the board?
No, so the MOSFET are the switches.
Oh, okay, got it.
I need MOSFETs.
Alright, cool.
Yeah.
Yeah, I even went ahead and made some things to like hold specific wires and stuff, but it's kind of like the main thing, would be to get a power PCB so we can merge. I think we can remove the bus bar and minimize this thing. And the other cool thing is that right now we have wires going from, we have, each servo has, power wires and PLVM wires, and those go different places. So it kind of like, it's a very complex routing. If everything went to a single board, that would be like way easier.
Yeah, let's talk about that, because I do have some thoughts on all of that. I'm going to grab the screen, if that's cool.
Yeah. Let me, how do I stop sharing?
I think I'll just steal it from you.
Alright, steal it.
Okay, cool. Can you see this?
Yeah.
So this is something I shared with you a little bit a while ago. This is a little bit modified to that, and a lot of this has to do with like expanding to future designs, or just not having to redesign something in the future for something that we did now. So there are two options. The first one is, let's make something that only works for V1, and we can kind of get away with that. But in that case, I almost just prefer having the wire mess and just like trying to mechanically zip ties and just wire everything.
Sure.
But if we are going to design something, which I think we should, what I'm thinking right now that needs to be the architecture is one voltage line for the 5 volts, which your computer will use. In the case that you're using Arduino, you're not going to need 5 amps or 6 amps. The problem is, as soon as we want to switch over to a Raspberry Pi or anything like that, the Raspberry Pi 5 has a spec for 5 amps.
Wow, no way.
Well, so that's a peak current, right? It's not actually going to be that most of the time, but the power supply that they recommend is 5 amps at 5 volts.
Wow.
So let's just pretend that that's fine. Like, we can probably test it by plugging it into a ohm meter, or an amp meter, just figure out the power consumption that way. But that's that thing aside. The other voltage rail we need is 7 volts. And there's two options here. The first option is, say, screw it, let's not use 7 volts, even though the servos want 7 volts, and just use 5 volts for everything. But that just means that we have to beef up this guy. If we wanted to split it, because at higher voltages, we'll get better efficiencies on the servos and just higher forces available to you.
Yeah.
Just the way these servos work. We can essentially create one board that puts these two things together. So in this diagram, I had it as 2 different boards, but I actually think you can put these two on the same board and pretty much the same surface area, if not a little bit more than the one that we have in our, the one that we got off Amazon. I will say probably a little bit more, because just more surface area allows for easier thermals, and like we don't actually have to do AC relations. We can kind of just use rule of thumbs and say, okay, cool, that's more than enough, and we won't need to like really hyper optimize. We can in the future, by the way, to reduce these things, but we'll also in the future know exactly what our power is based on the motors we want to use, and so we can reduce the size quite a bit based on that.
Okay, and oh, go ahead.
No, go ahead. Yeah.
Oh, I was gonna say, like, these DC to DC converters, are they as big as our current one, like the inductor and two switches, I guess, or
Yes, but the nice thing is that everything is smaller. So um, you can use different packages for chips that come in different sort of, I guess, planar surface areas and stuff like that, but still allow for the same power throughput. So with less expensive components, typically, you'll get more simple packaging, which will just be larger for larger power, but with more complex packaging, you can get smaller surface areas for the same amount of power. And that's just a function of like laptops and phones and all this stuff these days. They all are pretty power hungry, and you need to be absolutely miniaturized for that. So there's a whole bunch of offerings for like off-the-shelf chips that you can get that are super high power throughput, but with a pretty small footprint. And that's what we want to use. So we trade off a little bit of cost for that, but in the long run, like we're paying, I don't know what was the price for the buck converter. I got three of these things for I think 18 Canadian dollars, which was pretty good in my opinion.
it was I paid $10 for one. I got ripped off. Yeah. Yeah.
But mine might also be like completely garbage because they might be using like even worse stuff than what yours has. Either way, the margins on these things that they're selling you are super, super large. Like if you made this yourself at the same volumes, you'd probably see that the actual cost of making this thing is way less.
Interesting. All right, so we should sell these. All right.
Well, you know, take one step at a time.
Wait, actually, I want to show you one thing. Let me send you a link here so you can put it on your screen. But it's kind of funny, I think. I'll put it in the chat here in the Hangouts. So I did also a layout. It doesn't look as nice as yours, and obviously it's not meant for a PCB. It's just meant for what's actually in the robot right now. But I think there's a couple of features here that we should make sure we maintain. Primarily, one is so I've added a switch so we can turn it on and off.
Yep.
So we should have a switch, and this is probably a good place to put it. And yeah, and the other thing is like we also have a voltage monitor here, right? So what would you suggest for that on the Power PCB, or how are you thinking about that?
Yeah, we could go fancy or we could go not fancy. The fancy way is to actually put essentially a voltage sensing component on the PCB that gets read by some microcontroller and reports back. There are actually power regulation or power converters that have that capability built into them. So there's something called the PM bus, I think. So the PM bus is an open standard that people have designed for power critical components. It's used a lot in automotive, I believe, also a lot in aerospace, but that's something I haven't really explored. I think pretty much what it is a expansion of I2C, or maybe it's a reduction of I2C communication that only allows certain features so that you can like be very safety critical. Because power components are safety critical in applications like cars and stuff, right? So we could select a chip that has that capability, and I actually have one that does. And then in that case, that chip actually does the voltage sensing for you. So in the case of adding a voltage sensor, the reason, and maybe we should ask, what's the reason you want the voltage sensing?
It's mostly so my battery doesn't get hurt. That was it.
Yeah. Okay, so the nice thing about all of these DC-DC like buck chips, they will have something called an under voltage lockout, which essentially means once you go below that threshold,
oh wow,
the regulator just shuts off. It's
really?
Stables. So you can, a lot of these components, sometimes they're fixed under voltage lockout, so we just need to pick a component that has a under voltage lockout that's configurable. And that's usually done by just setting up few resistors to certain values.
Oh, cool. Yeah, I mean, that's one way of doing it. I guess it will just like stop working and we will not know why. Because like the smarter way would be for it to know it's low battery and they tell you it's low battery.
Yeah. So if we wanted to do something like that, what becomes interesting at that point is I could slap a very simple microcontroller on here that interfaces to the. Well, first we can either pick a component that has the PM bus capability, and then we'll just have to learn how to communicate over PM bus. But I'm pretty sure it's just I2C, so any like the Arduino can do it, the Raspberry Pi can do it, the Jetson or NAND can do it. So it's not like something that we wouldn't be able to interface with any computer with. It's more so just, do we want to build that capability ourselves, or should we just pick a component that has it? I would say pick a component that has it, but we might pay more for that, just in general. So we can take a look. Like I think we can consider different options and see what our best solution is.
Yeah. What microcontroller are you using for the build? It's just a Pi, right?
So I'm setting up a Pi right now with the AI hat. The Raspberry Pi has this new hat called the AI hat,
Yeah.
which I think we should be able to use. And then it's going to, so the Pi only has 2 PWM.
Oh, okay. Let's see.
I don't know, how many does the Arduino have?
14. 13.
Okay, yeah, wow, that's actually quite a lot.
Sorry, 14. There's a 0 one. 14. Yeah. So there's 14 digitals, and then there's like 6 analogs. So I was gonna say just connect the power PCB to the microcontroller for it to read the voltage
Okay,
from it.
okay, hold on. So you're using the digital outputs and just, you can configure any one of those digital outputs as a PWM output?
Yeah. So I mean, this is an off-brand Arduino, but it says digital and then like between brackets PWM.
Okay, perfect. Yeah. Okay.
So
If you just turn on and off digital outputs that are not PWM outputs, that wouldn't get you the actual timing that you need, right, on PWM?
yeah, I don't think so. Like basically.
I don't think so. That's what I was confused about. I haven't used an Arduino in a while, so I'm kind of out of the loop on what its capabilities are. But that's actually really impressive. I think there is another part of this discussion, which is how do we really, like, if we're going to use 7 volts, the PWM signal is not 7 volts, right? So we still need to send in a regular PWM signal into the servo, which whatever.
Wait, why not? Oh, because it's coming from the microcontroller, right?
Yeah, I think so.
Okay, yeah.
So, what I think would need to happen, and I'll go back to my diagram.
Oh, you need to amplify it? Do you actually need to?
No, you don't need to amplify it. What I'm saying is we would, and again, this could be one board, but just to like functionally differentiate right now, you have the computer that talks over I2C, and this essentially generates your PWM signals. Those PWM signals then will, like, you have your high voltage rails, let's call it high voltage even though it's only 7 volts. You have your high voltage rails, and then you have your PWM signal, and they all go out to a header that looks like, bring in this guy. So this is the 16 channel PWM thing that I need to use because the Raspberry Pi doesn't have capability. And I think I'll bring up the web page for it too.
Yeah, I remember this guy.
Right. So essentially, you can see what's going on here is that it's got PWM on like the top, and then you've got V plus and then ground, right? And that's just generally how those servo wires work. They have yellow, red, brown, and yellow is PWM, red is plus voltage.
Wait, are you holding the servo box, the shoulder?
Yes.
Oh.
Yes.
All right, cool.
So this is what I'm using, by the way, to try to get the simulation to match to like the actual response.
Oh, nice.
Yeah. We can talk about that later. This is about the power.
Yeah.
Okay. So in this case, what would happen is we would essentially have one board that takes as the input the PWM signals wherever they're being generated, whether it's on the Arduino or it's on this like separate chip, and then it takes the high voltage line from the PC-DC converter, and then you can now arrange that PCB in whatever way is most convenient, so that you can just plug in your servo headers and then route the wires whichever way you want.
Yeah.
So that is what I was thinking would be an expandable solution, in the sense of, in the future, if we want to switch these servos out with more modern servos, which are speed controlled rather than position controlled, or using an actual FOC controller. Have you seen the Cheetah motor design? It's like this, super pancake style motor with the integrated.
Yeah.
So if we want to switch to that, it would be the same architecture. You wouldn't change that architecture. You just get rid of the PWM, and you'd just be passing the voltage or the high power lines directly to the motors.
Right. Yeah, that makes sense.
Okay, so those are my general thoughts on like what the architecture should be. So in this case, I think there's two boards that we have to build, right? One board is the power supply, which probably includes both of these things, and then the second one is like an ease of use, like distribution board, if we don't want to use bus bars. So for example, one of the big things that's probably causing a lot of wiring mess is that you have to route a whole bunch of things to the bus bars and then route them back eventually.
Yeah.
So instead of that, we could actually have a stack up where like the power supply sits on top, then you have your like distribution board with headers going to the side, for example, or maybe it's a little bit bigger and like the headers kind of like stick out the sides.
Yeah.
So you just like plug in vertically, and then we could even do something where you have the computer that's sitting underneath all of that. So like everything sits on one stack, and then how you had the two different compartments between the top side of the robot and the bottom?
Yeah.
You just expand that a little bit and like have everything kind of more center of mass.
Yeah, that makes sense. Okay.
So, if we want to do that, I think we should start, or at least from what I can do pretty quickly, is I can start designing, and I guess spoiler I already have, but it's more so we can kind of choose the components ourselves, and we'll kind of go through the entire process again just so you can see it. But we can put this into one board, and then we'll decide on like what the best, form factor for this other like distribution board is, where it combines the two things, and then you just have to plug in the headers. The other thing, by the way, is this board is going to most likely have to be assembled by somebody else. By assembled by somebody else, I mean the components be put on and soldered and everything. Because of the types of chips and components we're using, mostly surface mount stuff.
Yeah, I just assume like JLCPCB would just assemble it, or no?
They can, yeah, exactly, yeah. So that's going to be more costly for us. This thing, I honestly think we could do ourselves, just because there's going to be a whole bunch of through-hole headers. Like we just order bare PCBs, get them in really quick, and then just solder the tubes.
Okay, I see.
That'll be pretty easy to do.
And wait, when you say expensive, is this like how expensive?
I don't know yet, but
okay.
I don't think.
Like, because like, is it because you're going heavy on the copper? Because like.
Yeah, so it's going to be 4 layers at least, and you're going to go heavier copper. So in terms of, I think you could still get it built for. I still think the majority of the cost is eventually going to end up in the components that you have to buy. So
okay.
The production of the PCB itself, if you're only ordering 5 PCBs from JLC, for example, it will be relatively expensive just because you're producing it for 5. But then, I don't know if you've ever tried, but if you just increase it from like 5 to 15, the cost goes up by like $3. There's like a big cliff for the first 5, and then it's like a really, slow increase until you get to like really high quantities. And then they get to different pricing schemes entirely.
Right. I've never tried.
we can try. Okay. So I'm going to stop sharing my screen real quick so I can get set up on the KiCAD stuff, and I'll
okay. Wait, so what are the next steps? Basically, you're saying 2 boards. I'm gonna write this down. So 2 boards decided for a 2-board design. So one board board number one is it's like a basically battery to DC for with a 7B and a 5B DC line. And then board number two is connects to board number one.
And the computer.
And the microcontroller, yeah, computer, and all the servos connect to it, right?
Yeah.
So that board handles the power and the PWM signals.
Yeah.
All right. And this design will scale as we move away from cheap servos, quote unquote cheap. We've spent hundreds of dollars, but
right. And by scaling, I mean, you know, we're gonna have to change the design a little bit, so we're not outputting 7 volts anymore, for example. But that's a very easy change.
Okay.
To, like redesigning the whole architecture for the house block.
Okay, cool. Makes sense. Okay, board number one likely needs to be assembled by JLCPCB. Why can't we assemble this ourselves?
We can. So the big reason is that most of those components will be surface mount, and a lot of these high power chips have pads underneath the chip itself. So if you don't have any like precise way of detecting that if that solder has actually been attached properly, you can blow up the chip as soon as you power it on for the first time.
Interesting. This is probably why.
This has way more like precise tooling for pick and place. Like for what we would have to do is I would have to sit there with tweezers, and after I put the solder paste on with the stencil, you'd have to like get a microscope and just like try to align it to the best of your ability. Then you toss it onto a hot plate or an oven that does a specific temperature profile, and then like it melts all the solder and attaches all the components. But it's not like if your pick and place procedure isn't precise, then you could get like wonky components, and that's what eventually causes it.
Man, I thought like if you brought a hot air gun and like the solder, it would kind of like just shift in place. No, it's like.
Well, most of the time it does.
Yeah.
Like
right.
you could do the heat gun method, but you just have to do that like for the whole board. And so what we're gonna end up doing is making really large pads of copper, or like just really large fills, I guess you can call them, of copper inside the PCB, which means you're just completely sinking all of that thermal heat. So you just need a lot more heat. On your
interesting.
Usually damage components, and it becomes a mess.
Interesting. Yeah. All right. Makes sense.
But I do have a hot plate, so we could try. We could just order like all these components and give it a go.
Now I'm scared.
Yeah, I'd almost rather JLC assemble this, and we'll see what kind of cost it actually ends up being.
Okay. By the way, in terms of size, do you have any sense of how small we can get it to be?
Yeah. What's your? Let me grab the power. What's your? Is your buck the same size as mine? The one that you got from Amazon?
Yeah. Yeah.
Mine's 60 by 52. 56.
Let's see. So mine is 60 by.
Yeah, it's gonna be the same.
45.
Oh, okay. Yours is smaller.
Well.
Wait, the heatsink? The heatsink is 45.
No, just the board.
But mine's still bigger than because my board. The board looks like it's 50. Or no, 48.
Oh.
Yeah, and then the heatsink is 52.
Yeah, my board is 45 for sure.
Okay, I mean not that different. We'll take a look at some of this. I think, like I said, if I'm clever, I think we can get it to fit in this angle. You might need to go a little bit bigger because we're putting 2 buck converters on the same place essentially.
But they're smaller bucks, right?
Yeah. So what's happening on this board? If you take a look, the controller is actually on the back side.
By the way, your skin keeps blurring. Oh, okay. I see. Yeah,
Yes.
mine looks the same way.
Yeah, and then only the power components are on the other side. So
Yeah.
it's the exact same on yours. So we can do the same. We can have that kind of split where the controller sits on one side and the power stuff sits on the other side. But the actual inductor and capacitors they're using. So first, they're using all electrolytic capacitors. They're these big can-looking things. We're going to use ceramics for a lot of our design. We're going to have one big electrolytic on the input, just because when you plug in a battery, you should just have a bulk capacitor there to kind of sink in the inrush.
Right.
And just allow for voltage transients on the battery. But other than that, batteries are pretty clean. So the rest of everything can be ceramics. They're like super tiny components. The inductor will be huge no matter what you do.
Oh.
But it can also, the way they've done it here, I'm wondering why they did it this way. Maybe it's just the way that this inductor works is they kind of went sideways, whereas the inductor that we're going to use is going to directly attach the output for the 5 or 7 volts. And so, you know, these things could be on the side here. This heatsink could be not as huge, and you can kind of like lay everything out so that in the same surface area you get essentially the same like 2 box, but maybe a little bit bigger. That's really what I'm trying to do. But that's the goal.
Okay. Cool. Yeah. I mean, the space is very tight. That's a concern, but yeah.
But we can also go vertical. We have more vertical room, right? So like if anything, we could do 1 buck, 2 buck power distribution.
Wait, why do you think we have more vertical room? I don't feel like we have room anywhere.
I mean, if you share your screen again, we can take a look. It seems like it.
Okay, wait. Let's see. I'm gonna resume my presentation here. Sure. All right. So yeah. So man, like what I was saying is like I don't like these. So eventually, like if we were to keep the same vertical distance, I think that's fine. And then, but eventually the legs will need to attach to the center of these, right? We need to center these because right now.
Yeah, so that's fine. We could like just bring the whole box kind of upwards.
Yeah.
So it's centered, and then like make some nice like curve, you know, edge.
Well, so I had more curved edges, but curves make it so the space inside is really like it's not utilized properly.
Yeah.
And this looks huge here, but in real life it's actually kind of tight. If you need to like,
What's the dimension, for example, between the battery and the edge of the other one? Like where the bus bar is. Like if you were to say like between like the outer edge of the bus bar and the battery, the inner edge of the battery, what's that distance? Doesn't have to be super precise.
It won't be super precise. 52 millimeters.
Okay, so perfect. That actually is almost exactly what we had, right, for our buck converters.
Oh, you're saying it could fit in here? I mean, sure.
No, it could, like, essentially what I'm saying is that I don't think we're going to need those bus bars. Like, that bus bar is super huge, right? So
right.
we designed the power converter so
I see.
the bus bar kind of built in.
I see what you're saying, yeah.
Replace that entire thing with the power stage and then just wire through the holes.
Yeah, and so these guys can go away. I wonder if the Raspberry Pi will fit in here. Probably not, but I guess...
Oh, no, for sure. I think the Arduino actually looks way larger than... What's the size of that thing? I'll tell you the Raspberry Pi.
Yeah, I guess I need to move away from Arduino, actually. So this is 53 by...
I honestly think it's fine for you right now to use your Arduino just for, like, motion, like testing all the motion and like, mechanical stuff, because it's the quickest.
53 by 68. Yeah. I'll move away eventually. Not now. I literally just got a second Arduino like today.
So I'm reading 56 by 90 is a Raspberry Pi. So
it's bigger.
It's a little bit bigger, but like I think that's okay because if the buck converter goes to the bottom side, I think that makes perfect sense.
Yeah. Okay. And then the other thing I actually wanted to do eventually was. I wanted to test if this battery is big enough or too big. So I was just gonna put this on a treadmill and just like walk. See how far we can walk with this battery.
Yeah. Do
No. So I was getting into that, but like right now I cannot run the robot without it like catching on fire because of the thin wires.
Yeah.
Um, so that's the next thing. So I'll do that on Monday.
Okay. Sweet.
Yeah.
All right. Yeah, but generally, I think it looks awesome. By the way, Ignacio was saying he liked the look of it. You watched your video.
Oh no, that's a lie. Can't say he likes it. This is not nice, man.
The legs look nice.
Oh, the legs, sure.
Okay. Do you want to get started on power supply design?
Yeah, take us. It's all you. Take the screen.
Here we go. Sharing screen 2.
All right.
So, by the way, I think it was you who asked me at one point, like, what's a good electrical engineering book for fundamentals?
Okay.
And I honestly don't think there's a good textbook for fundamental electrical engineering because there's 3 different things you can do, right? One is the art of electronics. That's a very famous one. That will tell you a lot about electronics, but nothing about high power systems or power transformations, unless you're talking about very low level stuff or low voltage stuff.
Yeah.
So my suggestion is to actually just find. We'll go through 2 things that I think are very helpful typically. One is that there's a lot of information out there on whatever for electrical design because it's just really easy to describe once you kind of know what you're looking for. So in this case, we're talking about DC to DC converters, and back in, I think it was 2000, early 2000s, Texas Instruments published this white paper, or it was maybe a more paper, but this is a really good overview of everything you really need to know about the theory of creating DC to DC converters.
Interesting.
So we're going to take a look at one of the diagrams here, which again, we will just go over the basic operation, and then it's almost immediately, we're not going to do any more theory, we're going to go right into practice, because I think really that's probably the best way to do it is see reference design, and then try to copy them and say, why did we do certain things? So in this case, the way that all DC to DC converters work, it's kind of a misnomer because there's a lot of AC stuff going on, or just things that cause the nice line of voltage we usually think of to turn into something that's jaggedy and rippling and all that kind of stuff. And that's why DC to DC converters don't actually have a perfect DC output. It's good enough. It's just the voltage. There is a voltage ripple. You have to sometimes design for that to allow for the voltage ripple. So what's going on here is you have your power source here on the left. It's just, let's say it's battery. Then you have 2 switches. This is called a rectifier. Sometimes, in this case, they're talking about a synchronous rectifier, which means you actually have 2 switches.
Wait, I see 1 switch.
Switch number 1?
Yeah.
Switch number 2.
Oh, okay. That's the switch. Okay, all right. I see.
So,
that's the symbol for switch.
There's another switch that's going to ground here.
All right. Oh.
If it was or I guess you'd call it an asynchronous rectifier, this switch would not exist. It would just be a diode, and that still actually works to rectify the signal. Essentially, what you're doing is you're turning the DC input into a rectified signal, which just means that you're kind of making it more triangular, or you're only passing some of the voltage through at some times at a certain duty cycle, so that you can then filter that rectified signal back into a straight line, or close enough to a straight line.
I see where this is going.
50% of the time, let's just take the duty cycle. 50% of the time, if this switch is closed and this switch is on, then you're passing 12 volts, let's call it a battery voltage 12, to this line, and that goes through, I don't like that they call it an averaging circuit, but it kind of is. It's your regular LC filter, right? So you have current that is ramping up in your inductor as you have this switch closed.
Yeah.
And that current is then going to also be stored in this capacitor. Then the second half, let's call it the second 50% of the duty cycle, this switch opens and this switch will close, connecting the inductor and the rest of the circuit here to ground. So now energy is being dumped into ground from the inductor. So like your current is kind of going downwards, and the voltage is actually being supplied by this capacitor to the output. So when we're thinking about it in terms of like really slow times, this wouldn't work because like you have a really large voltage ripple and like your voltage would be going up and down. But if you make these switches turn on and off really fast and time it really precisely, you can get a very specific like 12 volt input to 7 volt output. And that's how all of these DC-DC converters work. Most of them. There's other types, but this is generally how it works. And then the way that you actually turn on these two switches in the correct timing is a control circuit. And that control circuit is something we really don't have to worry about because the people who make these chips are so good at it that they can kind of give you like a reference design for a certain voltage you want output, and then you can kind of follow it and you'll be fine with it. You don't need to understand like the fundamentals or like the really...
Yeah. Can you go back to what happens when switch number 1 is open? Sorry, closed, and switch number 2 is open.
So switch number 1 is closed.
Closed. Yeah.
You want it closed or open?
Closed. Yeah, it's closed.
Okay, so closed, and then switch number 2 would be open.
Yeah.
So when switch number 1 is closed, you have your battery, let's call it, or your DC input.
Yeah.
Connected to your LC circuit.
Yeah.
So you're taking energy from your DC input and charging this LC circuit. You're charging the capacitor, and you're also storing energy in the inductor.
Right.
So you're storing energy in both of these components.
And so what happens? So obviously, okay, my input voltage could be 12 volts. What would be my output voltage when switch number 1 is closed?
So you're thinking, I know where you're going with this.
Okay.
You're thinking in terms of very low frequencies. So if you just close this and this was the circuit without the switch here, just open loop here, or open circuit here, you would eventually get 12 volts on your output.
Exactly. Right.
Yes. Because your inductor is just a short circuit after a certain time, or not a short circuit, but like it's just wired.
Oh, but before that certain time, it's like a lower voltage going through, right?
It's a ramp up.
Okay, perfect. No, this makes sense. Okay, yeah.
So you're essentially, and what will happen is you're taking your output, which is like the actual voltage you want on the output. Let's say it's like 7 volts. This is going to read, it's going to be like, oh, we're going up from, let's say we've never turned it on. It's going up from 0 to 1 volt, to 2 volts, to 3 volts. And then this is essentially a PID here.
Yeah.
And so, hold on a sec, we're getting really close to 7 volts, so I'm going to turn off the switch and then allow it to like, do a little bit of that.
That's interesting. I wonder, because I've measured our buck converter using a voltmeter, right, which is not great for high frequency movements. So I wonder how noisy it is. It's like
we will take a look. So Texas Instruments, by the way, I think TI is a really good place to find reference designs for a lot of these like power components because they really put a lot of effort into documentation. So for example, this like variable output 80 watt heating element power stage, they have all of the design files and schematics and everything for this power stage. That was just an example. They also have some tools for determining temperatures for all of their chips, but we won't really look at that because we have some nice pictures. When we're talking about waveforms, though, this is a boost converter, so it's the kind of the opposite. So instead of going from higher voltage to a lower voltage, just doing the opposite, but the theory is the same. And you will see that the waveform...
You can see some overshooting there and some noise.
Yeah, so that's your general second order response, right? Because you got an LC circuit. So I'm trying to find where's the... this is input voltage.
Are you worried that this could damage the computer? Because no?
Yeah. We're going to design it so that the output voltage ripple is super low, or like low enough that the Raspberry Pi won't care. Because remember, all of these computers also have their own regulator, right? So if you plug in 5 volts, they actually linearly regulate down from like what you're providing in down to cleaner 5 volts. So they already have some filtering on their side that we don't necessarily need to worry too much about. And that's true for any other device that you orchestrate. see if I can find an output voltage. Oh, this is a startup sequence. So if you take a look at, so what's going on here is you have a this is a boost converter, but they've kind of offset it so that you're going down to a different volt, or like being minus here.
So what's a boost converter?
You're taking the lower voltage and going.
Oh, got it.
Buck is take higher voltage, go down. Boost is the opposite. You'll actually see sometimes that those two things can be one device. You can actually have a buck boost converter.
Oh yeah, I thought the mechanism, the circuit would be different.
It is, but you only have to add 2 more MOSFETs to allow for that. Essentially, instead of it being before the inductor, you have it after the inductor and the capacitor, and then other stuff there in order to connect it.
So is the theory that you load the inductor to a higher voltage kind of thing, or?
Yes.
Okay.
Exactly.
Yeah. Okay. That makes sense.
That's exactly it. And I'm trying to. This is actually a buck boost reference design, so maybe let's open up the schematic.
We're getting off track here, but I was just curious.
We are, but this is kind of again, there's a lot of things you can do to optimize your design, but my premise here is that a lot of these designs already exist, so we shouldn't try to go hyper optimal, because there's a lot of thermals you can consider, a lot of voltage replacing, all that kind of stuff.
Interesting. Yeah.
Figure out, but
it's a good point.
You just don't need to care about it as much.
Yeah. Yeah, I like this. I didn't know TI had all this stuff.
Yeah, TI is great. I highly recommend looking at some of their documentation, because as you'll see in the other document, we'll go back, they actually have thermal tests that they've done as well, which is really cool to show off. Like, this is what actually gets formed in a buck converter.
Yeah.
Okay, so this is their controlling chip. You can see they have these 2 switches, which are the buck side switches, you can call them, before your massive inductor. And then you have 2 on the boost side. So depending on how you switch all 4 of these switches, you can either get buck or boost.
Yeah.
And that's how they do it.
I see.
Okay, and then just really quick, I do want to show off the thermals. But this is the startup sequence, so you can see how there's obviously a transient. So your input voltage goes up really quickly because that's just your input voltage. So whatever, like your switching, your physical switch, let's call it, would be. But the actual regulator takes some time to get up to its regular value. Okay, so let's take actually this is still in this document. This is again a TI document. So they did a whole bunch of testing. They show off efficiencies and stuff like that. The other thing here is really just showing off some of the temperature or thermal readings they took. Which having a camera like this, by the way, would be really cool.
Yeah.
Where do you got one? So this is the inductor. You can see that is getting very warm. The switches on this board are just all around here. And I don't have a good picture of it unless they have it.
You know, these cameras are kind of cheap on AliExpress now, right?
Probably.
Yeah.
But you can see here, inductor, this is the big inductor. These are all the switches for this specific design. And everything here, the reason they put all of this stuff right next to each other is because they want all the warm stuff together with a lot of heat sinking available. And by the way, you can also see that there is no heat sink on this.
I was going to say, yeah.
Because the PCB itself is much larger, and they have likely multiple layers, all with higher density copper.
So the copper is the heatsink.
Right, the copper itself is the heatsink. Along with these vias, so vias are just holes that you make in your design, which will allow for air to naturally kind of flow through there. Or self-induction, I guess is that called? Or no, self-convection, right? Where the hot air causes the air to move away and refills. So that's what I wanted to show you on this side. So this is the general understanding of what you need to consider generally for power supply design. It's what voltage am I coming in with? What voltage do I want on the output? What kind of imperfections can I accept on that output voltage, and what kind of thermals do I need to handle because of that?
Okay.
By the way, when you step from a higher voltage down to a lower voltage, like let's say you're going from 24 volts down to 1 volt, that is going to be less efficient than if you're stepping from 24 down to 12.
Yeah, for sure. The greater the gap, the less efficient, right?
Right, and that's because there's two things. The first one is it's called switching losses, and then the second one is current ripple losses. Those are the two main like driving losses. That's why the inductor gets hot, and then the switching losses why.
Actually, this is because of switching losses, and also you said rift. What?
You can call it current ripple losses or the inductor loss. It's the loss in the inductor because the current's going up and down and causing transients that aren't doing meaningful work for you. They're just like wasted. By the way, this is the same for like how the drives on motors work. Because they're switching, there's like 6 MOSFETs that are switching to get you your approximate sine waves with your motor drivers. Their losses are primarily switching losses compared to conduction losses. Like conduction losses are also something where you're just losing stuff because of the copper that you're using.
Yeah.
But generally, switching losses are pretty significant in anything that's high frequency or high power.
Okay, it's cool.
Okay, so now let's take a look at some of our options. So we know that we're not going to go past 6S, I think. I don't think there's any reason to. 22 volts, 24 volts is kind of like a nice area to be in generally for components. So I kind of discounted some of these higher voltage TI things, and I've been saying how good TI is, but I actually found something that's not TI, because there's a lot of other companies that make power stuff. I just think that TI documentation is the best. There's two. The first one is this guy. It's, and this is what I mean by the chip has pads underneath that can get pretty gnarly to solder.
Yeah.
This is the first one from MPS. This is technically a 30 amp capable system, and it can output up to both 5 and 16 or 5 and 7 volts. Its highest input though is 16 volts. So if we take a look at the data sheet, this is the other thing, by the way, is every data sheet for these controllers, that is really the textbook that you have to use to design these things. So I'll see that it will give you very specific application information as well as sometimes PCB layout information that will just guide you through the whole design process.
Nice.
But if we take a look at this, so the input is 4 to 16 volts. We're going to be using an internal bias. I can explain what that means later, but it's not really necessary. It's just if we plug in a pin to an external power supply for the low voltage stuff, or just use its internal bias. Sometimes less efficient to use internal bias, but for our case, it doesn't matter. 30 amp continuous output current per phase. The nice thing is you can actually like sequence these two, like you can create 2 phases, so essentially double up your buck converter and then have both of them supply the same voltage rail. Usually you don't want to do this because the 2 converters will then compete against each other and have current being drained into the other inductor from one side to the other, and that's like a huge problem in a lot of designs that do multi-stage or multi-phase. But we can get 5 and 7 volts out of this. We obviously wouldn't want to use this thing for the 5 volt buck because this is like super overpowered for that.
Wait, how much can these handle on the input?
What's that?
How much can these handle on the input?
Up to 16 volts.
So it's not enough, right?
Well, if we go with 4S, it would be enough, right? What's 4S? It goes up to...
Yeah, 24. No,
6S goes up to 24.
yeah, you're right. 16.
Yeah. So
16 and a little bit.
4S, but I agree this is not ideal. The other option that I found, and this one is a little bit more attractive, is one of these guys. And actually, for this guy, there's a higher power version, so we can get a 12 amp at 28 volt input capable. And we can, what I'm thinking here is instead of having 1 buck, we actually have multiple, and each one supplies a different voltage rail to different servos. That is not as flexible of a solution, but it is a little bit more easy to design for in the sense of power, because we can choose which servos get which power from like which buck, right? So like we can be a little bit smart about this and say that we are able to use, all of the legs get power from this first buck, all of the other guys get power from this other buck. Now the only problem with this guy is, like I said, this one doesn't have any option for that PM bus that I was talking about. This one does. So this has PM bus 1.3 compliant. That means we can talk to this thing. And if I take a look at the systems diagram, you could kind of have something like this where you have I2C communication going to this design.
So it sounds like to me like you would prefer to use smaller bucks, right?
I wouldn't mind using this one. This one actually is interesting. The only thing, and maybe I need to do a little bit more looking to actually find a more appropriate one, because there's so many options, so we can maybe do a little bit more looking on that. But the reason I like this one is if we wanted to have that communication to it, we have that option. And secondly, we would only need one of them, which is just easier to lay out in general, whereas like 3 will intrinsically need more space. The only problem with this one is the voltage. So maybe if we can find a higher voltage one that's similar to this, we could make it work. But when you start going to 24 volts and then you also ask for 30 amps, the actual power throughput becomes way higher. So your cost goes through the roof, and that's the other downside to this. This thing is $9.6 Canadian per unit, whereas this guy, even the higher powered version, is $1.61 per unit.
Wow. Okay.
3 of these guys would actually just be cheaper, just straight up than
I see.
this chip in general.
What about the TI one? The first one did you?
So the TI ones are very interesting. So this one is, you can use this one for the same purpose, like to control 2 FETs, as long as your FETs have the appropriate like transient response to be able to be turned on and off quickly enough.
Yeah.
You can use any of these controllers to make that work. And the only question there is that they haven't said that you can use this design, or they don't have a reference design for this guy to allow for that. So you can see I out maximum is 30 amps. So you can use it for that purpose. And this thing is also kind of expensive, but not that bad. I mean, if we're only using one of them, it's like, it might be worth it. These are the general things that we run into when we talk about.
Yeah, I mean, I'm just asking, but you do whatever.
$5, right? So like $5 is less than $10 for the MSP. So we could do this, right?
Does this have PM bus, or I mean?
No, this doesn't have PM bus. That's, I think, part of the reason why that other one is more expensive, because I think it has like all sorts of integrated, like it has a microcontroller essentially integrated into it.
I see. Man, I don't know if we're gonna use PM bus, but I mean, it's up to you. You decide. Because yeah, I don't know. I don't know about using PM bus. Sounds complicated, but I don't know.
Yeah. Well, I don't think it's too complicated. It's just like more effort. I think what we should do is maybe have this guy design a buck that doesn't have integrated like communications or anything, and then we'll just update the design for V2 or whatever that has communication built in with just a separate microcontroller.
Okay. A lot of promises for V2.
That'll be an easy addition. I could also crank that out. Like we could just add a small, like essentially an Arduino that communicates with this thing, or like does the voltage sensing at the same time.
Yeah. By the way, if we don't have voltage sensing in V1, that's fine. I can keep the same voltage sensor that I already have. Yes.
Well, so the other thing we could do, for example, is just like if you give me what the interface for that voltage sensor you have is, or we could just have like headers coming off our power supply, like just debug headers, and then you can just connect your voltage sensor to those debug headers.
So this guy connects to the charging connector, to the balancing connector on the LiPo.
Oh, I see. Okay, so that actually, That's actually very specifically made for the.
Yeah. Trying to find it. I don't know where I put it.
I'm sure we can get beepers that are just like, hey, detect the DC voltage that you're reading, and then beep if you're lower than a certain.
Yeah, you can't actually see the PCB on this one. It's fully wrapped, but.
Well, in that case, I mean, because the battery already has that output, I feel like just catch it for this one.
Yeah, exactly. Yeah. So maybe forget about that. Let's keep it simple.
I actually do like using this guy here, the LM25149. They always have weird names.
The TI one.
Yeah.
Perfect.
And you can see what it's gonna look like in the end. There's a lot of extra space here that's not needed. They just usually do that for like.
Wait, they don't have dimensions here.
This is gonna be pretty small. So this chip itself, we can kind of like estimate, right? This chip itself is like 3 millimeters across.
How many?
3. I mean, we can check the dimensions.
Wait, so
5.5 by 3. So its width is 3, its length is 5.5.
so they have the IC. So they have the back as an IC.
The controller and the gate drivers are both in this IC here.
Okay.
And these are the 2 switches, low side FET, high side FET, and this is the inductor.
Okay, so it is a board. It's just super small.
It's pretty small. I mean, this is 5.5 across and 3.5 in length, and I don't think you need anything beyond like this curve. It's right here.
That's great. All right, I like that.
So, and again, with additional like thinking on how, like, so this is all on the same side. So the controller and the switches and the inductor are all on the same side. You don't want to make the switches and the inductor on 2 different sides usually. You want to keep all that on the exact same side, but the controller could actually go on the opposite side, and that's not a problem. As long as you're not like overheating it because you're putting it right underneath or something.
Okay. And then you need to add like a XT60 connector for the LiPos.
Yeah, we can do XT60. Just there's vertical ones, I believe. So
Yeah.
if I take a look at DigiKey, I think we have surface mount or even through-hole at XT60, right?
Yeah. I'm gonna stop interrupting.
No, it's okay. It's okay. This is probably like the most tedious part about like any of this design stuff. I think the most tedious part is really just figuring out what components you want to use. Once you know what components you're using, it kind of flows really easily.
And if we're going with JLCPCB, how do you know they're gonna have these components?
They won't. Most likely they won't. You have to, but they have a nice service where you actually, on their webpage, you tell them what parts you need and how many, and then they order it for you.
Oh wow.
You just pay a bill to get them to stock that component specifically for the project, and then once they get it in their inventory, which takes some time, but that's just how it is, you can then tell them to produce the board and assemble it.
I had no idea. Okay.
Yeah, JLC is pretty nice. They have, I think, the best interface online for producing.
I even thought they had their own PCB design software or web portal.
They do. They have something called EasyVDA.
Yeah, that's it. ECDA. It used to be everywhere on YouTube years ago.
So this is one of the ones that I was telling you. I think I still want to explore like what its capabilities are because it has gotten better and it seems like it's fully featured now. But they do have a full integration with JLC, which is really nice. But I don't know. The other one, by the way, is this thing. I've been seeing a lot of ads for it. I don't know how good it is. Apparently they use like Copilot of some kind. But as with all design CAD software, I think the one that you know how to use
Right.
is the one that you use for the designs rather than trying to learn something new, unless you have time. But this might be the way to go if they're like making certain things that are really tedious automated. I'll show you some of the more tedious things here in PCB design. You'll see firsthand while we go through that.
All right.
Okay, so anyway, JLC real quick. The first thing I would do is JLCs. That did not do JLCPCB.
We're gonna bring a drink.
Yeah, sounds good. I came prepared with my drink. I don't know if you can still hear me or not.
All right, I'm back. Sorry.
It's all good. I was telling, I guess, the camera that I brought my own drink.
Oh, nice.
So
Oh, water?
We're less prepared, I think. Okay. But in general, just going over JLC stuff, all you have to do is upload the BOM. If they don't have something in their already, pretty expansive inventory, you'll essentially go through part sourcing, which is like an online portal within their website that helps you just say, I need you to source this part for me. And then they will say, you have to pay this much, they get it in, and then you can say, okay, cool.
Cool. By the way, I guess if someone doesn't know, JLCPCB.com is a website.
Yeah.
They make custom PCBs. They have a lot of other stuff, not just PCBs anymore. They do CNC, 3D printing, and they have a lot of hardware, kind of like McMaster. But they are Chinese, so it does ship from China. So it can take a week or two to get parts.
Yeah, exactly.
But the price is really good.
When we're talking about, for example, TI parts, if they don't have the specific TI chip that we're using, then TI will have to ship it to JLC, and that might take time depending on where specifically this manufacturer is. Now, TI, I think, is global, so or they at least have global warehouses now at this point. So I don't know if it would take that long, but and some of the TI stuff or some of the other stuff is already stocked on JLC.
Yeah.
Mostly, like if they have to source a part, that might take some time, and then you're only allowed to kick off the build once they have all your parts, so that you can assemble the whole thing without them interrupting their assembly line. Okay, so the design software I'm using is KiCAD. It's open source, pretty nice, I would say, quite featured. It's a little bit quirky, and you just kind of have to get around the quirks. So I've already created a project folder for this, and essentially what a project folder looks like is just all of the files for the schematic and the layout, and then I usually create two folders, one called fab and one called lib. Inside the lib subdirectory, we'll put all the footprints and parts that KiCAD doesn't already have in its library. And inside fab is where we'll generate all of the fabrication outputs that we need to tell the manufacturers how to produce this thing. And generally, the way that PCB design works is you first do something called schematic capturing, which is, I don't know, they make fancy terms for this. It's literally just writing out the schematic in the tool. And then all of the components that you've listed out in the schematic, you assign footprints to, and then from there, you do the layout of all those footprints and then connect them in.
What do you mean you write this schematic? Well, I guess you're about to do it, right?
We're about to do it, yeah. So I'm going to open up the schematic file, which is just the .KiCAD_SCH. It looks something like this. There are different page templates and different styles of page you can use. I'm just going to stick with this one because it's the default one, and I don't really think we need to care about a lot of this title page stuff for this. But if you wanted to change those, you go under page settings. The thing that you do want to check out usually is schematic setup. This tells you how some of your stuff is going to be set up in terms of each component will have certain parameters. There's some default parameters that we'll see, but in order to make your life easier with generating bombs, bill of materials, uh, I'm pretty sure everyone knows that, but
Yeah.
it's a bit of a loaded term. The field name templates is where you add in these extra parameters. So these will be like the manufacturer part number, what the manufacturer's name is, maybe the data sheet link, and some other notes that you might want to put in.
This is just for yourself, right? It's not like it's gonna pull any information from it.
So some information is pre-filled out by the library. Sometimes when you grab symbols and libraries from other companies, for example, companies will say, here's my KiCAD library for all the components
Oh, I see.
itself, or like for this individual component you want to use. It will come pre-filled with some information, but generally you want to make your schematic follow the template that you are using, so that when you generate the bomb, it always comes under the same columns. Like, so all the columns are filled out. And we'll see what that means in a second. But typically, the four I always add in are manufacturer part number, manufacturer name, so we'll just call that manufacturer. And then sometimes I like to put supplier link. So for example, on DigiKey, if I want to remember exactly which link it is, because sometimes the part number won't be entirely descriptive because there's like extra packages, like package configurations that will not be a part of the MPN and stuff like that. Then I'll put the supplier link, and then I'll also put notes. Just in general, for example, if I need to remember something when I make a PCB layout, or when I need to tell the manufacturer something about this component that might not be obvious. The other things you can take a look at, which I wouldn't change, the defaults are pretty good, are the electrical rules. So there's, similar to in 3D CAD, there are automated checks that you can do for like interferences and full alignment and stuff.
Nice.
In electrical schematics, you can do checks for pins are not being connected, or like not all of the things are attaching properly. There might be, if you do schematic capture correctly, you actually can assign functions to pins, saying that this is a power pin and this is a power pin. So if you attach two things, one power pin to like a logical pin, then it will say, hey, by the way, why is this power pin being attached to a logical pin?
Nice.
Like that. That's violation severities, and like you can ignore them for a warning or for an error. And again, all of this stuff, there's just a whole bunch of like preferences we can set. I wouldn't change the defaults. Defaults are pretty good at that. So now that's done. Their schematic capture is literally just creating a schematic. So most of the time, because we're just adding resistors, capacitors, inductors, all of those things are included in the library. This button right here, or if you just press A on the keyboard, will open up KiCAD's like pre-built library. And by the way, you can also create your own libraries of components that you use often if they're not already in here, and then just like set it as a global preference. But I typically don't do that. I just use project libraries, meaning I'll just pull in the new symbols and the footprints I need specifically for that project, because then I can package the whole thing and send it to somebody else without having to worry about them having to connect to my library that's on my computer.
Makes sense, yeah.
And this is taking way longer than it usually does.
Yeah. So is this just opening the library?
Yeah, it's just going to open the libraries, and maybe it's because I'm screen sharing or something, but this usually does not take this long.
By the way, it's HiCAD as in HiCAD, right?
No, KI.
KI.
Yeah.
KiCAD. That makes way more sense. All right.
Yeah. So, okay, the first thing I'm going to go over really quickly is this library you can use to add all these components. There's like a lot of stuff in KiCAD. The most recent version of KiCAD, is adding a lot of the most commonly used components, so you'll find a lot of the stuff without even having to look. But generally, if I'm looking for a resistor, I'll just find the resistor, and this is, instead of this squiggly thing that's usually like used in paper, KiCAD just uses box. And that's fine. So if I double click on this component, it brings up the component properties. And what this is those parameters I was talking about. So you can see that it's already got general parameters associated with it. So it's always going to have a reference. This is the ID of this component. So as soon as you add more resistors, it can be R1, R2, R3, and that's how you kind of define which resistor is going to be assigned to which manufacturer, product number, and so on.
I see.
So it's the ID that is kind of universal between the layout, the schematic, the BOM, everything will get this ID. And then that'll be a way to organize everything. The value is going to be like how many ohms is this thing. The footprint is going to define which footprint, like what is the the footprint shape, I guess, of the actual resistor that you're using. So what do you need to put on your PCB to allow it to connect to this resistor? Data sheet is always there. You can like create a link to a data sheet. Specifically, you don't usually do this for resistors, capacitors. You'll do this for that TI chip, saying like, here's a very important chip that you need to understand, and you need to understand this design.
Yeah.
Reading comments there. Description, I'll show you how I usually do this, but it's good to like put in the description straight from DigiKey or like wherever you found that component, because those descriptions are nice and well formulated. And then you'll have your manufacturer part number, manufacturer, and then these two other fields that you might or might not use. So let's take a look at now, because again, we're gonna have to go back to the data sheet. The data sheet for this guy, and as I said before, TI is fantastic with their documentation. In all TI data sheets, you'll find a section, and this is true for a lot of data sheets, by the way, they will always have something called application and implementation or application notes section, which will literally walk you through an example design. And they'll give you all the equations you need to calculate how much capacitance you need on the output, how much inductance you need, how much, I guess, current you're allowed to pass through, or like what the ripple current will be estimated. So there's a bunch of math here. I typically do the math after I figure out what components I need to use, because it doesn't really make sense to work the other way around, mostly because if you keep scrolling down here, you will see typically a table.
Wait, what is this math for? Why are we doing math?
To figure out how much capacitance you need, how much inductance you need.
Oh, I see. So the circuit is not... Okay, so the values in the circuit will change depending on your application.
Right, exactly. And this is where the bulk of the actual surface area comes from, right? But the chip is tiny, but we have to fill out the rest of the circuit to actually make it work.
Okay, and there's no button in KiCAD that just takes this layout and just puts it there?
No.
Alright, cool. Great.
So, hey, actually, if that is something that somebody could work on, that would be fantastic, because that is one of the tedious parts of this, is to actually take a look at this. You can see right here, right? So you've got application circuit 1 with this regulator. It's running at a pretty high frequency, so automatically I know we're going to be running into high switching losses, because you're switching these things at 2.1 megahertz.
That's high?
Yeah, super high for switching power performance.
What would be low? Like kilohertz?
Yeah, 200, 400 kilohertz is like pretty nice and low, easy to.
I see. All right.
By the way, higher switching also means higher electromagnetic interference, so you have to be a little bit more careful about that if you're like trying to also put logical circuits very close to this.
What's the frequency on something like a Tesla motor?
The motor itself, or you mean the driver, like
the driver, yeah, the inverter, yeah.
Oh, geez, I don't know. I think it's gonna be about a megahertz.
Okay, so it's high also. Okay.
Maybe lower. I don't know. I think you could probably find that answer. Somebody's done a teardown. I'm sure
yeah. I just said just on top, but yeah, sorry.
No, I wish I was not kidding. Okay, so the nice thing is you can kind of, typically when you scroll down far enough into the TI documentation, they'll actually just walk you through an example, right, of what you would want to do. So you can say like the input voltage range is 8 volts to 18 volts. This is not exactly ours, but we can just modify these values differently. And then what you want is, what is my output voltage? They want to do 5 volts output current at 8 amps. If you go down, they'll actually do all the calculations for you, saying like, okay, cool, your inductor, let's see, this is output capacitors. So your output capacitor should be 47.4 microfarads, right? It's going to be greater than this number. That's what they say. So in order for the switching to properly get to the right levels, they give you a number here, and they show you how to do the calculation. So this is the really nice part about all of TI stuff, because they always go through these things with you. And then the final thing they do, which I think is really good, is they actually provide some test data or simulation data based on that design that they gave you. So you can see how this would physically work if you plug in an oscilloscope.
Wow. Okay, that's really cool.
So what I like to start doing is I like to take a design that they already have, so I can start putting all the components into the schematic, and then I worry about putting the values, because I will do a sweep of choosing what component it actually is and choosing what values they are actually. So, for example, in this case, they have a 440 kilohertz synchronous buck breaker. So, like I said, 440 kilohertz, right? This is kind of more normal, you could say. They want an output voltage of 5 volts and then a rated load current of 10 amps. And I want to make sure that this can actually handle 30 amps, because we said that somewhere, but I don't see them designing for it. That's the other thing that you kind of have to check.
Up to 42, right?
So 42 is the voltage. We need to check how much current they can handle. And most of the current, by the way, is not going through this chip, right? The current is actually going through the Q1, Q2, and the inductor. But there might be some current sensing that has a maximum, right here, I sense positive lightning. So they have a shunt resistor here that does the current sensing, and that will limit how much current can actually pass through your design without this thing not being able to work. And that typically happens, or that sometimes is said at absolute maximum ratings, these are all voltages. I sense positive. You see that here. It's so this is, like I said, this is the most tedious part, is picking your components. Once you have them picked, it becomes clear. Okay, this data sheet does not say anywhere.
Wait, are you sure that shunt resistor, that's where the current's passing? Like, that's not part of the IC.
Yeah, it's not. So, but what's going on is that this is essentially reading the current, right? Like this iSense Plus is going to read the current across this pin and this pin, likely, just because that's the two that are right across that resistor. And so you need to be able to make sure that whatever resistor you choose, first of all, actually that would not work in general, because this is for 12 amps. So whatever this resistor needs to be able to handle the power, essentially, of your output in order for this to work. So that's why I'm curious. You'd have to put a massive resistor there. Where was this was the actual page, right? So it does say I out maximum is 30 amps here.
So out maximum 30, doesn't say in, but in it will be lower, obviously. Okay.
Yeah, it'll be slightly lower on the input because the voltage is higher. But what is setting that limit is confusing me. It's got to be that resistor, because that's the only thing that takes the current. Okay, so let's do max. Okay. Let's just search for maximum, see what we find.
There's a
these are for the yeah, that's different. Those are for the that's not cool. And maybe here we can see, so load current. Yeah, so they only go up to 10, which is really interesting because in this they say the I out maximum is 30 amps, but the testing they've done.
Well, what's load current? Isn't load current going in or going out?
No, load is your output, like what you're supplying out. So this is an efficiency math. You're saying that at 10 amps, if you are providing an input voltage of 24 and your output is 5 volts, then your efficiency is like 94. Or 94.
What happens if you control it for 30 amps? Does anything come up in this data sheet? Did they mention 30 anywhere?
I can try just searching for like 30. Just gonna put that in again. Oh, it's page 30. 30 megahertz.
There is one.
Where?
If you go back to the table. Yeah, here, if you go up, it's oh, actually, but that's not amps. That's something else.
Yeah, so, yeah, that's the that's oh, that yeah, just does not matter right now. Okay, the other thing that TI does that's really good, and maybe we should use this instead, is let's go to their online tool for helping us select chips from theirs. And I think we should be able to actually just straight up see if they can suggest a circuit for us. I use this sometimes it's not that great, but a lot of times it gives you the right direction. So what's our minimum input for voltage on 6S?
It would be 16.8.
16.8. Okay.
Yeah, at 2.8 each cell.
And then what's the high end?
It would be 25.2 at 4.2 each.
5.2. Okay, and then we want to do. Let's do the. I'm less concerned about the 5-volt buck just because it's super low power. But 7 volts and let's say 30 amps, right? That's what we kind of want to aim for. 30 amps is the maximum. We've already discussed this, that 30 amps we're probably not going to reach continuously. So
Dude, I don't even remember where that 30 amp number came from, but
I remember where it came from. So I took a look at the servo online, and then its typical application is those RC cars, the steering.
Oh yeah.
And then the power supply for that was rated for 5 amps, which, you know, if we have 12 servos and 5 amps, that's more than 30 amps. But I don't think we actually need that much.
Right.
It's only if the car or if the servo stalls and we still keep pushing. So
yeah, that makes sense.
We can probably get away with much less than that, especially because, like, imagine if you have 2 feet in the air and like 2 feet on the ground. The 2 feet in the air are not going to be drawing nearly as much current as the ones that are having to push off the ground, for example.
By the way, on that note, this is very unstable when it's only on 2 feet.
Okay.
Yeah. Even 3, it's kind of like, you know, I wouldn't stand in 3 legs for too long.
Okay, they are using LM25119. That's interesting.
Wait, can you go there and like export that circuit?
You can't export it. You can ish, but you can't put it directly in. You still have to read it. This is interesting. This is slightly different. So interleave just means you have 2. This is like multi-phase, similar to multi-phase.
I thought you didn't want to do 2. It's bad practice.
Well, it's not bad practice if the chip has like communication between the 2 things. The chip has to be able to do that essentially.
I see.
And this is specifically designed. This thing, I imagine, is very specifically designed for that purpose. So LM25. This looks like it's going to be pretty expensive though. Yeah, $11.
Each one, right? And we need 2?
We would only need one of these if we do 30 amps. Although they convert choose a much less expensive chip because it's only one. Oh, there is a programmable current limit to this one, so we can actually just like limit the current output of this guy so that we don't blow anything up, even though it kind of depowers it a lot.
Okay.
Okay. Here. Oh yeah, this thing is.
Man, that's gonna take forever to draw.
Well, what I'm gonna do is I'm gonna show you. I think because if we try to go through the whole process, it would actually take a really long time. So what I'm gonna try to do is get like a very simple circuit in, and then I'll show you the process of like writing the PCB layout and all that, and we kind of do that kind of just as a tutorial right now, and then I'll go back and actually put in the details. So maybe I won't do. I think it's good for us to select the stuff on
for sure,
so that you know what I'm picking, and like we can kind of like talk about the design that, but the actual implementation of this is just like put on some headphones.
By the way, I find it interesting that you think $11 is expensive for some of these things.
Oh, it's super expensive. It's like that's $11 for the chip, but the actual like board will be expensive. Like it'll have cost and the placement, the labor for doing the placement, and all that stuff.
Like what, $40 total, or?
I don't know. I mean, at volume, it'll be much less than that.
Yeah, I mean.
The problem is you have to order a minimum order quantity of 5 from JLC the first time you do it. So you're paying $50 straight away for that, for the chip. This chip only. Then
minimum 5? We need 5 minimum?
The minimum order quantity from JLC is 5.
I see, okay, now I understand. I get it. Say no more.
Yeah.
Yeah. It's expensive.
The next thing is obviously you have a few spare in that case if something does blow up, so you can kind of like, but the problem is if something does blow up, it's probably a design problem. No,
well, basically every price you gotta multiply by 5 to get a set. Okay, great.
But you also get 5 PCBs, so you're not like actually paying 5 times more.
No, man, I always tell myself that. I always end up throwing them away.
What was the other suggestions on this page? I wonder if there's something that's not included. If there's a one-off. So this is interesting because it says it's interleaved, but its nominal efficiency is 7.7, which would literally just blow up. So I don't know why. This is what I'm saying. It's sometimes not very good. Like, why are they even suggesting that? This would literally, I think, blow up if you try plugging that in. There is. Oh, why did that happen? Oh, come on. Oh, there we go. Okay. What I'm going to do is...
It's getting more complicated.
Yeah, this is getting more complicated. I'm going to have to do a little bit more thinking about this. We might actually want to just go back to the other one, this guy right here, and then like do the separate voltage rails. I'll think about that a little bit more, but I do think that we could use this guy. This is not that complicated of a design. You just need twice the components. The only problem with this is that you need the area that allows you to have this inductor. This inductor is not small, right? It's like 159 millimeters squared. So you have 2 of these because you essentially have 2 buck converters kind of operating the same way. But you do get 30 amps of continuous current output.
I didn't realize it would be so hard to get this much power.
There are other solutions. It's just more so like, picking the component is going to be the longest part.
Actually, random idea, but have you looked at the buck at the IC on the bucks we currently use?
Yeah, I have. They're I think they're using analog devices.
Mine is a TI. It says LM.
What is it?
So I'm trying to read here. It's like super small. 25116 LM25116.
Yeah. So this is a previous version of this one, right? If it's 25116, this is 25119.
Oh, okay.
How does it? Okay, hold on. Let's find out what that actually looks like. LM25116.
Sorry, LM25. No way the camera is gonna focus on that, but yeah, I'm pretty sure it's LM25116.
Where did mine go? I had it with me for like a second.
Well, you bought like 5, so it doesn't matter. Just grab one from the pile.
That's actually a really good idea. Let's see what this is.
I mean, I just assume
Board, by the way.
whatever they did, it was like we could definitely improve on, but
That's a great idea. Okay, let's see. This has got to be it, right? Mine's different than yours, by the way.
what do you have?
Hold on, I need more light. Mine doesn't have indication. But okay, if it's this one, this is also a buck converting chip, so it must be.
I just googled it and it took me to the TI's website.
Yeah. I'm just opening up the data sheet. So it goes up to 42 volts, yeah. So it's the same family. So I do think we could use this. The same as like why I think we theoretically could use.
Is it cheap? No.
This is the cheap right here.
I mean, like, is it? What's the price?
It's $7.
Oh. Wait, how? Like, I paid $10 for the entire thing.
No. That's because we're looking at the price on DigiKey, right? So like when these guys buy it, when you go to like, they're buying it in like thousands of quantity. So as soon as you buy in thousands of quantity, you get a much lower price on this. Also, you can, in terms of like economies of scale, when you're a manufacturer, you're also buying like other things from TI. So you can say, hey, listen, TI, I'm buying all of these things from you. Just give me a bulk discount on all of them. And that's how you like reduce unit prices much.
By the way, what's your unit price? I can't read your screen. It says 7.
It's 7.12.
Oh, okay. It's kind of small. Now I can see it. 7.12. Okay, cool. Yeah, it's 4.
2,500 at like half that price if you buy 2,500.
Yeah, it's 4.6 for me USD.
So yeah, Canadian dollars might just be like way more.
Yeah, that's inflating the prices, I think. But still, I agree. It's not cheap. I agree.
I mean, but we could use this, right? Like I do think that that's a really good idea. I like this idea because we have one of these things, and this circuit is the simple one that I like, which is the basic synchronous one. And I like to keep things pretty simple.
Cool.
So okay, let's go through some of the stuff that we need to do. The first thing is, okay, so you can see how this is like kind of the circuit that you'd have to create. But all of these are like, these are super small capacitors. They're just meant for extra filtering. And if we scroll down further, they probably have a layout. Consideration. Yeah, there you go. So this is what it's going to look like, right? So like if you take, the way I generally determine like how big something's going to be is based on these images. So this controller is about the size, like approximately the size that you need it. So if this is on the opposite side or the back end, it can fit in the same footprint. And what's the length of this controller? It's super tiny, right? It's 4.40 millimeter width. Does that make sense? And either way, it's gonna be like between 4 and 6 millimeters in length, let's call it. So if you kind of like take this and then look at it, it's twice the, like you can fit 2 controllers in the same width, and then you can maybe fit 2.5 in the in length. So like compared to what we're looking at here, you know, the bulk of the thing that we can actually
All right.
So, okay, let's go back up to the application circuit though. This is what we're going to recreate. And the first thing we're going to need to do is, because I don't have a symbol for this, you can actually get the symbols and the footprints directly from DigiKey. This is most often the time what I do. You just go to under EDA and CAD models. And then for most things, especially popular things, you'll see that you get a symbol that you can just plop into your schematic, and then you also get a footprint. So I'm going to download them. They have all of the different formats.
Wow.
I'm going to grab a step file and KiCAD 6 files.
Does KiCAD use the step file as well to create a 3D model?
Yeah, so you can create 3D models, and most PCB design places or like software will do this. And again, this is why I'm kind of interested in some of the newer ones, is if they can like make this process smoother, it saves a lot of time. So
Yeah.
what you need to do is now essentially take the download folder, the downloaded zip folder, and imagine you have like a whole bunch of different chips that you need to do this for. It becomes super arduous. Go into lib.
I think what's interesting is that it's almost like you're drawing it first. It's almost like the opposite of like a mechanical part where you model it first and then it draws. Here you draw it first and then you lay out the PCB later.
Yeah, exactly.
It's like
you do the theoretical schematic first, and then it helps you generate the PCB layout essentially. So now that that's in there, I want to get the symbol and I also want to get the footprint. So I'm gonna just add a project library. I'll call it LM25, and then I will find the path. So the nice thing KiCAD does actually, if you're creating these project libraries, it will actually let you do local references. So everything, like I said before, you can just zip the folder and then send it to somebody else, and they have all the information.
Yeah. That's really nice. That's really nice.
It would be nice if, again, there would be some sort of like version controlling, like GitHub.
Yeah.
Just I think you could just toss all these files into GitHub, but some of them are libraries. So to import the symbol, you just have to find the .KiCAD underscore symbol. Open that, it'll find the right symbol in that case. So that's going to be added to the project. And the other thing we have to do is, it's super interesting. Give me a second. It's amazing how things don't run as nicely when you're like recording the screen or something.
Yeah, this happens all the time, man.
Okay, there we go. And then the other thing we want to do is go into preferences, manage footprints. And the same thing, there's a library of footprints. That's why if the component already exists in the KiCAD library, it's nice because the footprint is automatically connected to the symbol. But in this case, we'll have to do it manually.
How do you know they didn't have it?
Good point.
Yeah, you didn't check.
I typically just say, screw it, I'm just going to add the ones I know are like the custom versions of the chip.
Okay.
And what you need to point to is a directory called that has a .pretty name. I don't know why they call it that, but you just click that folder and that has the footprint. And same thing.
What they call it? Pretty?
It's just this is the folder that we downloaded.
Yeah.
If you go inside, they typically have a step file, and then under your KiCAD 6, they'll have a .KiCAD underscore symbol file. That defines your symbol that's going to go in your electrical schematic.
Yeah.
And then pretty is the folder that contains all the information for the footprint. And realistically, that's actually just in these files here, but KiCAD P6 and beyond just takes one folder with a .pretty suffix, and that will essentially import an entire library. So for example, actually, if you had a whole bunch of different components, one library could be held in one folder in this case. And that's why they did it, I think, but again, I don't, it's just the quirkiness of the particular CAD software. Okay, going back to the schematic. So now if we go to add R symbol, and I hope this doesn't take as long as the class. There we go. Okay, and I just look up the LM25, and this is where we'll find out that it was already in the KiCAD schematic. So LM25119 is already in there, but ours was not.
Okay. Yeah, I guess it's different.
It's different, and that's why getting the custom symbol is sometimes nice. So if we take a look at this guy, it's going to give us all of the important pins, and one of the things that we might go back and do, because it saves a lot of time, is if there's any pins that are not here, but they are in the footprint, and we need to assign them to ground, for example, they're not just no connects, then we want to probably just add it to the symbol. So that'll teach you like how to create custom symbols or just like edit symbols that already exist. But this is essentially our, maybe I'll zoom in. I don't know how well you can see this, but let me know if it's like super blurry.
Now I can see it great. Yeah.
Okay, but we added this in, right? So if you take a look at, if I zoom in here, you will see the exact same pinouts that they show in this map.
Right, yeah.
So now we can literally just go.
Actually, it's not the exact on the right side. I mean, the order is different. There's an EP.
Let's see. EP is 21, but software, or not software, switch.
Oh, I see what happened.
HO is 19. So you can see how EP here, EP is going to be one of these bottom pads.
Yeah.
Actually, EP is going to be the single bottom pad, because this package only has one bottom pad.
Got it.
And that's going to be connected to ground for us. And actually, you can see right here. EP
yeah.
Yeah, here it's right there. Okay, so now it's just a game of putting in all these things. The other thing that we actually do need is the FET and the inductor. Those will also be custom packages, but I think because we're already kind of like running long, let's get through some of the layout here, or like let's get through some of the schematic, and then I'll show you the process of bringing it into the layout, and then maybe we can continue this another day, because it's definitely going to take more than like a couple hours to finish this design. So if you want to do it on camera, yeah, we'll just have to figure it out.
Okay.
Okay, so let's just start putting components in, and this is you're gonna watch me.
Yeah, that's fine. I do a lot of that repetitive stuff. By the way, like, are all resistors the same? The brand doesn't matter? There's no like cheap resistors and expensive resistors? I imagine there has to be, right?
There are. And so there's a whole world that we haven't talked about, which is choosing footprints for resistors. So actually, something that you typically want to do is take a look at some of the notes in the data sheet to figure out what power some of these resistors need to be. And if that power is more, so there's higher voltage requirements sometimes, and there's sometimes higher power requirements for resistors. Voltage doesn't matter, but their power is dependent on their size.
Yeah.
The standard footprint sizes that you always use, and I'll show you some of them right now. See this way. So if I go into the footprint library for this resistor, and I search up resistor. Actually, what I usually search up is the actual name of the footprint. So the footprint name for resistors, capacitors, sometimes like LEDs and diodes and stuff, are based on 4 numbers. Those 4 numbers define the size. So a very common, like larger form factor is 0805. And I believe, I forget exactly what dimensions they are, but they're essentially, I think, the length and the width in some sort of like 0.8 millimeters by 0.5 millimeters or something along those lines.
Okay. And bigger means it can handle more power?
Usually bigger means higher power rating, but not always. You can get 0805 resistors that are 1/16 watt capable, or you can get them at 1/4 watt. You get them out. Probably not higher than that. Generally, an 0603 or an 0402, so those are smaller form factor resistors. They won't go up to the higher power values. So you'll still have some option there. I and that's based on the actual manufacturer part number that you pick, rather than the footprint or anything like that.
Okay, I see.
So if I take a look, it's just, one of these things, and maybe what I'll do is, let's take a look at the PCB side of things too, because that will be more interesting here than watching me do this. It always takes way longer than you expect it to initially. You're like, oh yeah, it's gonna be way easier, but then it turns out.
Well, I didn't have any expectations. That's why I wanted to see you do it, because like never done it, so
Yeah.
no clue how long it could take. I guess I was expecting things to be more streamlined and not like, oh, I have to copy these schematic. But there's also a lot of parameters here that I had no idea about.
Yeah, a lot of this stuff is to make it kind of easy for you when you eventually go to generate the bomb. But you can see how, in this case, it didn't autofill the custom parameters, but it autofilled some of the other parameters. And obviously, this doesn't make any sense. So typically, what I would do for this component is I would go back to DHT and then just copy some of the stuff over. So
Oh,
this is
wait, what was there before? What didn't make sense?
It was just like the same thing in the value copied over. So
Oh, I see.
a little bit more descriptive. Sorry, copy it right here, put that in the data sheet. And I won't put the data sheet for everything. Like I said, you only need it for your most important stuff. Manufacturer part number, this is obviously what's the most important. The manufacturer is also important. That is, these two things are typically required by most manufacturers, or most assemblers, so that they can find the part that they source it for you.
Yeah.
And supplier link and node I don't really care about it now. The other thing that I did was I added footprints to this guy. Yeah, and then let's actually just do a bit of connection here so that I can show you some parts of the way this works. And generally, by the way I like to do things is power comes in from the left, goes out to the right, and then higher voltage up top, ground down below. That's just like standard schematic design or schematic layout.
Okay, makes sense.
If you put ground on the top and VCC on the bottom, anyone who's done this before will just look at you like, well, why did you do that? It's like, okay.
Yeah, I would have.
You can absolutely do that, by the way. There's no actual, electrically it's the same, but conventions. So what we're seeing here is we have a V in, and then that V in is going to go through a resistor network here, R1 and R2, and get controlled by this is what I'm talking about, the under voltage lockout. So the UVLO is determined by this voltage divider, R1 and R2. So that's what we're going to set up right now.
All right.
We're going to do this, that, and then the first thing, or one of the other things you want to do is define your voltage input. So this is something called a net name. Net names are essentially just nodes on your circuit that you have special names for, so that you can kind of refer back to them through the layout process or anything like that. Some people say that you have to label all your names. That is or all your nets or all of your nodes. That's way too intensive. KiCAD will give automated names to a bunch of your nets based on what pin it's connected to, and typically that's fine. But for your V in, V out, your some of the more critical nodes you want to give names to. So we'll call this, what's our nominal voltage? Maybe between 16 and 20.
Nominal would probably be 21.6, 22 maybe.
Okay, I'll just say 22 volt nominal. Plus, just to give it a little bit of descriptive name. And then what I can do is, because I know that's my input, I'll just toss that up there. And these boxes in KiCAD, by the way, are what you use to connect wires between boxes or circles. So you can just click on them and then create your connections between them. So the network here is V in comes in, there's a voltage divider, and then we go to ground. You can add a ground connector.
Oh,
It's not a
ground has parameters too?
no. It's just a special symbol that doesn't have parameters.
Oh,
It's
okay,
like
I was gonna say.
a very commonly used symbol, so they have a different like place in the library to put that up. So you can see that's what we did. We did VN, and we'll have to add these capacitors, but again, like in electrical schematics, you don't actually need all of this to be connected exactly in this way. You could actually have this on a different page in your schematic, and as long as the net names line up properly, KiCAD will automatically globally connect all of them.
Oh wow. Alright. Alright, I
So
didn't
that's
know
the
that.
good thing about this is that you can create different pages and essentially organize it in a way that makes it a lot cleaner. So let's do it this way. I just need to connect this guy over to here. And let's say that's the circuit, right? That's what we need. The first thing I'm going to show you, which I think is nice, is the electrical rules checker. This is that automatic thing that goes through all of the rules that you set up and tells you like what you've done wrong. When we do this, don't show a lot of errors because it's saying that all this stuff is not connected.
Okay.
Which we know is a problem. I don't know what this is. Oh, okay, this is the other thing I was talking about. So input power pin not driven by output power pin. So the ground is a power component, so its pin on its symbol is defined as a power input, which is inputting power into it. But there's no component here that's providing the input.
I see. I see.
Which is telling you it's an error. But that's okay. It's not going to stop you from doing anything further. It's just going to tell you that those are the errors based on the rules that you've set. And there is an equivalent error checker for the layout, which is more important than the schematic checker.
What is this?
So the schematic page looks very similar, except you got a few different things, and this is where you have to start being a little bit more deliberate about the design, because this is what you're physically going to build. On the right side, you have a whole bunch of layers. In KiCAD, .cu means these are actual copper layers.
Okay.
And everything else is kind of either something that's physical or they're just notes that you put in. So there's like a whole bunch of user layers that are just meant for notes. B.fab and F.fab are just for additional information that the fabricators sometimes use. The courtyards are, if you have a component, the footprint might be like 2 pads, but the actual component might be bigger than those footprints. So we need to showcase like what is the courtyard that this component takes up so that we don't put other components.
Interesting.
Margins are not important. They're similar to courtyards, but slightly less. They're a little bit more lenient. They're not like physical boundaries. They're more sort of like, also don't go around this, right? Like,
yeah.
This is my component. I don't want anything else there. Or it'll release a lot of features from that. Edge cuts. This is what defines like the actual shape of the cuts that you need to make.
Yeah.
So this is your outer edge of the PCB. The mask is the green stuff on your outer faces, or the blue stuff, or the black stuff. Like it's the thing that you have your pads that are exposed, but then there's a whole bunch of copper on front.copper that needs to be covered, so it's not just exposed to the air. So that is the thing that covers that. That's called a mask. So you got one on the front and the back. And then silk screen is the text that you can put on there. The paste is what solder, like the automated solder machines will put this on there. And then when you do the reflow, it kind of like flows. So it's usually just right around the pads.
Got it.
Adhesive, this is typically not used, but if it is, then it's like described. You need to put extra adhesive to actually, maybe it's like for potting, like if you want to pot the entire board so that it's waterproof, or like additional adhesive that you have to put so that it sticks better.
Yeah.
That, and then the .cus or the copper plates. Now, this is for a 2-layer board. That's the default. If you go under board setup, this is where you can change your rules and your board layout. Under physical stack up, you can determine how many copper layers you want. So 2 is, that's like your standard PCB, top layer, bottom layer, and then that's it. You can go all the way, like modern boards are like ridiculously.
Each layer is isolated from each other, right?
They are, yeah.
All right.
And you'll see that here actually, because can see what happens. This actually shows you top down, right? So you got your front silk screen, that's the text. Then you've got your paste layer, then you've got your mask, then you've got copper, then in between your two copper layers you have dielectric 1. You can choose what kind of dielectric you're using, as well as the specific material and thickness. So this is where you set up your physical setup, and then, or physical stack up. There's also this thing called epsilon R and loss tam. These are impedance properties, which don't really matter for what we're doing. This is like where if you're designing a high data rate transfer circuit for like cameras or something like that, then you need to care a lot more about your impedance for each line.
Okay.
This is a power board. We're gonna do 4 layers, and we're gonna go from 0.035, which is 1 ounce copper, to 2 ounce copper on the outsides, and we're gonna leave 1 ounce copper in the middle. And the reason for that is the outer edges are really where we're gonna put all the power components, and we can always, like, we have a copper fill that spans all 4 layers, then we can always put vias and all that stuff to connect them, and then you'll still get most of your heat transfer to the outer layers.
By the way, did you say copper in pound? Sorry, in ounces?
Yeah, it's weird. This is a much better way of thinking about it. This is the actual thickness of like the layer.
Yeah.
So like if you have a copper area, and we'll see this in a second, you will fill up the area in the X and Y, but the Z is 0.07 millimeters.
Okay. I think it makes sense.
In ounces, I don't know where that came from, but that is like what a lot of manufacturers will ask you for, like how many ounces is copper? And there's a direct translation. It's just like based on the math of the copper you use.
I'm asking ChatGPT.
That's probably a good video.
So it's measured in ounces because it's a reference to the amount of copper spread over a given area. Specifically, it refers to the weight of copper that would cover 1 square foot.
Right. Yeah, that makes sense.
All right.
It's just a standard, like
Yeah.
there's no real. There's a direct translation. 0.07 is 2 ounce. 0.035 is 1 ounce.
Okay.
Yeah, good. Blinking, wonderful. So now that's updated the board properties, you can actually see the extra copper layers available to us now. They're in 1 and in 2.
Okay.
So the first thing I'll do is I'll go to edge cuts and create my edges.
Oh, cool. I was gonna say it's empty. Okay, no, it's not empty.
And then all of these things will have certain properties, so you can give it a certain size. So what's our desired size, let's say, for the board? It's 55 by 60 or something millimeters.
So we're matching the current buck, basically.
Yeah. So this is what it would look like. And again, we'll see how this will need to change. But in order for you to bring out, so once the schematic is done, imagine like everything is there. The nice thing is all you have to do is click this button and it will bring in all those components. It will also give you if there's any errors on like if a footprint is missing or like they can hide the footprint to the library. But now you'll see that all of these components, the footprints that we've assigned to them, are in your layout. They'll
nice.
I think there are add-ons, by the way, that because once you define your schematic, KiCAD knows which pin, like this pin on R1, is connected to this pin on this.
Is it connected? Oh yeah, I see some line there. It's very small.
Yeah, this blue line essentially says it's not connected, right? But what I'm telling you is that I guess there might be some add-ons or some like things that people are working on to like do automated connections, but automated connections are never that great because, especially for power supplies, you obviously want to do the layout in a very specific way to avoid thermals or EMI or improper, I guess, just inoptimal layout of like where the capacitor is going on.
Right.
So let's just toss this somewhere. Right.
I gotta bring it up.
Yeah, that makes sense.
All right, we have some stuff there.
Yeah.
Man, those
So
resistors look huge.
these are 0805 resistors. That they will be. This is why they're going to be large. You don't need 0805 for these resistors.
Okay.
Just chose them randomly. That's why they're there. But you have the chip, you have the resistors, and so the DRC, the design rules checker that I was talking about, is just this button right next to the pull-in button. And if we run the DRC, it's going to complain about a whole bunch of things. Mostly that we have two things that are unconnected, because in our schematic it shows that this resistor is connected to this guy, and then both of those have a node connected to this pin. So it's going to point out exactly where all those connections are. When you get to like really large designs, this becomes important, because like these tiny blue lines you pretty much never see. So if we do connect them, this is just like, get the trace tool, connect them, and now you actually have replicated your circuit that is in schematic in the layout.
Wait, you connected them on what layer?
This is on front copper, so I'm on front copper, and
what's front copper? That's above the mask? There's no mask?
this is, the mask would go above front
Oh, okay.
copper. It's not like exactly laid out in the same way, but you can see right here, front mask is there. The front mask doesn't show up on this view because you don't really need to see the mask. You actually want to see where the traces are.
Yeah, I just assumed it was in order, but yeah, okay.
Yeah. The other thing is you can go to view in 3D viewer and you'll see what's going on. So it doesn't have a model for this chip. We can take that step file that we downloaded and put it into this model, and you'd see it, but this would be your circuit at this point, right? So you can kind of inspect it based on like heights and all that kind of stuff in this way. It's a good way to visualize sometimes, but it can also be kind of weird to, or sometimes it can throw you off, especially if you have to brought in all the step files, because then you might see like, oh, like everything's kind of really small on one side, and then you put like massive capacitors on the other side and you realize that the board is actually kind of not weighed properly or anything like that. So if this was everything in our circuit, we could actually generate the files that we needed to in order for us to send this to a PCB layout or a PCB fab place, any factory that does it. And those are called Gerbers. Again, I don't know why they chose these names, but that's just the industry standard. I'm sure there's a reason. But everything that you ever need in KiCAD for fabrication outputs is going to be under both the export file in the PCB, let's call it the layout file, and the fabrication output. So the first thing that I usually do is I'll generate the Gerber files, and I'll point it to that fab directory that we had before. And I'll also create a new Gerbers. And by the way, it doesn't matter that all of this is happening now, because I can just go back and update the Gerbers. Like this is all like a workflow that you can do once, and then you can just overwrite everything over and over again. So there's no like deficit of doing this right now, just for showcase purposes. But in order for the Gerbers to be generated, you kind of have to take a look at what your manufacturer wants the file format to be. Typically, the standard will work for most manufacturers, especially if they're like a turnkey manufacturer where you just give them these files and they kind of figure out, and then they'll like ask you some questions like, hey, what's the, like we were confused about this specific part of the Gerber, what is that? And you'll kind of eventually work it out. For JLC actually gives you a guideline specifically, which I always have to look up because I always forget what they want exactly. So if you go to how to generate Gerber files, KiCAD 7 and KiCAD 8 are pretty much the same thing. But they'll tell you like what things to select here, and then they'll also tell you how to generate the drill files. So the drill files, the Gerbers are essentially what define each layer, one layer at a time, and the Gerbers are used by the automated system to like do the layers one at a time, process kind of test layer by layer, right? The drill file then, once that is done, will tell you the drills where to come in and drill the holes, whether it's mounting holes or vias, and they will get all these files, and we can actually, what we'll do is we'll say, want to generate the Gerbers for all of this. Sometimes you don't need to include fabrication nodes. Sometimes you do want to include it. Typically, I don't include the courtyards or the fab because it's just extra layers that the manufacturer doesn't really use anyway if there's nothing on them. Sometimes you want to include them. So in this case, we can include them, but you'll see there's no actual difference. But if we take a look at the JLC requirements, I think they don't like this. Okay, that's just different. They want no force plotting of invisible values. They do want to check the zones and fills. They want to use the old school stuff here, and then they don't want to use these series. So all I have to do is plot. It will plot all of the different layers. So each one of the layers is its own file.
Yeah.
Now in that folder. And then for the drill files, I think the standards are actually, generate the drill file and the map file. Sometimes you don't need both. Again, depends on what the manufacturer likes. Now we have that, we can actually go to JLC right now.
Oh, cool.
And get a quote for this. Not for, again, if you want it to be assembled, then you need to give them the BOM, which we haven't generated the BOM yet. But we can generate the BOM.
So this is a quote just for the board with no components.
Right. And you would have to do this anyway. Like you have to do this, and then you would separately give them the BOM to tell them like this is the bare board, and then put these components on there. And I'll show you what files you need for that because you also have to generate the pick and place files, and you can do that in the software. Again, it's just one button, but that is a separate sort of process.
Oh, okay. That's not on the Gerber, on the same Gerber files? No?
It's not on the same Gerber files. So I think, these are Gerber files. I think they like them in zip format, so you just have to, so if we take a look, all of those files that we just generated are there. By the way, you can actually view these Gerber files. KiCAD has a built-in Gerber viewer. So we can take a look at that in a second, but while we're already on the JLC thing, let's just send this to a compressed zip file, and then I think we just drag and drop.
Whoa, you can do that?
So maybe I put, you know what? I have to add it. Yeah, there you go. So it'll do its automatic processing of it. But you'll see, like, this is gonna be like, they're gonna be very confused as to why you're asking for this file because it's not actually written. So the shipping apparently costs $18, but the actual board, they're very confused. They don't have any pricing on the board itself because it's so simple. Here is where you give them the other information that you might have not given them.
Wait, that's actually kind of expensive, right? Is that for how many boards?
So this is for 5, but you'll see this is $7 for 5, mostly because they're kind of confused about it. I think it would be, if you actually design a board with only 3 components, I think it's not worth having them do it. Like,
right.
It's just something that, you know, you need to be, like, why are you designing a board with 3 components?
Yeah. Just do it at home. Breadboard.
The shipping is obviously going to be way more expensive in this case. But if you take a look, the PCB quantity here, it'll figure out most of these things for you. So the FR4 was the base layer that we wanted to use. That's like a standard PCB.
Wait, what does that mean?
What's that?
What is it? TR4?
FR4, sorry.
FR4? Oh, okay. And that's just like a fiberglass reinforced.
That's the fiberglass material. I don't know what the R stands for, but it's like the standard PCB fiberglass material.
It's a woven fiberglass cloth. Oh, okay, yeah. Epoxy laminate. Oh, interesting. Okay, literally just fiberglass. All right.
It's just fiberglass, yeah. Those are, and then they can do other types. Like you can actually do like copper core, which is like just a big copper plate. So if you were like designing super high power stuff, you might just want to use this. Aluminum. They have the flexible stuff, which is kind of nice. The Teflon.
Wait, what would you want? Aluminum.
Good for thermal conductivity.
And electrical insulation. LED applications. Okay.
Yeah, I guess LEDs sometimes are.
Oh, I guess the outside is aluminum, the inside is still copper.
Uh, no, I think this would be all aluminum. Well, I mean, maybe they have like one aluminum layer and then they do have other copper layers. I don't know exactly. I've never actually used that feature. That's an interesting thing to check out. Maybe it's like a good way to like build in heatsink so you don't have to buy more heatsinks.
Yeah.
Typically, aluminum is not a great conductor though.
Exactly.
If you're doing anything power related, which is kind of interesting because they're saying that you actually get more efficiency because you're able to move heat around more effectively. Because heat is one of the big things. Components derate and their efficiency goes down as that temperature goes up.
Right.
So if we do take a look at this, like the minimum order quantity is 5, like I was saying. If I toss this up to 30, I don't think it's my speed. Okay, that's interesting. They've added an engineering fee. So this typically happens when you go to higher quantities. What they do is they take your one board and they make like an array of it, so they can send one sheet that does like all of your boards on one sheet instead
Nice.
of having to like place it kind of separately. So
And that requires an engineering fee.
$24. But as you go up, I think that quantity actually just stays about the same. This is where it's going to completely contradict me. But I've built boards that are like, about this size that are power regulators. For you can get like 15 of them for $70, which is a pretty good price, I would say.
Okay.
But I think it's kind of confused because this is not really a fully functioning PCB. Besides that, so some of the other stuff, like if you're not working with JLC or like an online tool like this, where you get to dictate some of the other stuff, like, hey, I want a black silk or a black mask or a green mask, and I want my silk screen to be white. There's actually other colors available as well, I think. The standard is white. All of these things would actually be comments in your drawing file that you would send as like a PDF to your manufacturer or some other PDF or some other like Word document that describes all of these other things. So do I want 1 ounce or 2 ounce copper on the outside? Do I want 1 ounce or 2 ounce coppers on the inside? Do I need via covering? So like sometimes vias are just open, and sometimes you want to cover them with mask for impedance properties.
Yeah.
Things. All of these things you would essentially tell JLC to do. And if you weren't working with JLC, if you're working with a turnkey manufacturer, you'd actually just have it here.
Okay.
And then the stencil is another one. So you can actually say, I want to do PCB assembly as well. If you do the assembly, you need to provide the law somewhere. That's the next step, actually. And then the stencil is what they actually use. Like when you do the solder paste as like one of your last things before you do the in place, they will cut out a thin metal strip, like a very thin sheet of metal, with all of your footprints cut out, so that you can literally just have a machine go slap some solder paste, and then it will scrape it off, so that when you lift the stencil, the solder paste is on only these pins.
Interesting.
Aside those.
And you have to provide the stencil?
No, they will
Okay.
generate based on your layout file. So your layout file actually defines, and that's where your solder mask, where is it? F.paste. So these guys, if I turn the layer on and off, you'll actually see that each footprint came with a definition of where the paste needs to go. In this case, it's literally right over.
Okay, now it makes sense. That's pretty cool.
Yeah, so that's all completely automated. So right now, the biggest thing is really just putting all these components in, redoing the schematic, or redoing the layout to make it look like the actual board that you want. Then you have to add mechanicals, like we're probably going to want melting holes, 4 melting holes, 1 in each corner, deciding what connectors you want as the inputs and outputs. And then if you were really good and just very diligent about it, you do some simulations for EMI programs, especially for power. But I will go back to, again, because this is kind of time consuming, I think just going back to this sheet, this gives you all the information you need, right? So once you put all of these components in your schematic, most of these values will actually be the same. So for example, all of these 2.2 microfarad capacitors, they're essentially just providing a little bit of filtering for the input so that your VDN pin doesn't get overwhelmed with noise. And the placement of capacitors and inductors typically is very important, and the data sheet will say where you should put it. Let's see.
Like, why is it so important?
So capacitors, for example, in order for them to be effective, because every trace on your PCB is an antenna, theoretically, like nothing's a perfect, actual like schematic line, so to speak.
Right.
So if the capacitor is far away from the pin that it's supposed to help protect, or like help protect from fluctuating voltage or anything like that,
Yeah.
then you could actually get some kind of reflections that pass through to the pin, which then get amplified. Or you could have noise being injected on the trays right next to the pin instead of the capacitor actually connecting. So because nothing is perfect, like in a natural schematic, if this capacitor is here, electrically that theoretically just says, yes, I have that capacitance on this line, and that's the same thing. But physically, if this capacitor is somewhere far away, there's actually an antenna essentially in between that could inject the noise, and in fact does inject noise. So putting capacitors close to where they're supposed to be protecting whatever is important. And inductors, obviously, in this case, the inductor just needs more space, but I don't know if it shows us a layout example on this. Remember if it did. Yeah, so you can see what's happening here, right? So you have, around the controller it doesn't show, but your main power capacitors, your C-ins and C-outs, what they've done is they've created a very small loop between V-in to ground that's right next to the switches, Q1 and Q2, like pretty much right next to them, so that you're essentially protecting the V-in, you're protecting the current or the switches here from anything that's fluctuating on the input by these capacitors, and then you're protecting the output by these capacitors so that you don't create a big loop and create additional ripples in the middle here, and this filter actually works the way it's supposed to.
Right, that makes sense.
That's a big important thing. But the nice thing about TI and actually a lot of these other designs is they'll give you a layout example and just copy this layout example, right? Like this is what you need to copy to get to a baseline design, and then from there you can kind of optimize space constraints. So I'll give you one more example of this because other companies do this as well. It's not just TI. So this is the other one that we're looking at, and this is their layout, right? So you see the same practice happening here. Is you have these are your input capacitors, and this is your output capacitor, and you can see that the controller, in this case, because it has integrated, I believe this has integrated FETs, does it?
That'd be cool.
This one does have integrated FETs because I don't see any outdoor ones here. Yes. So the switches are actually inside the chip itself, right? And you only have to put the inductor on the outside. So in that case, you don't need to worry about where the switches are going, but you still want to limit the distance between, because this LX, these are like where the switches are going high and low. And then the filter is here, right? This is your inductor, and then this is your capacitor. So V out here has both the capacitor and the inductor really close by, and we're minimizing the area for the switching because that's what causes the big thermal, or the big EMI, as well as the larger the surface area where there's a lot of switching, you'll also get more conduction losses because of that.
Makes sense.
So, and they'll explain this, right? Like if you go to any data sheet, they'll say layout considerations. There it is. LX pins and pattern connected to internal low side switch drain. Near low resistance thermal conduction pad, most noisy switching node. So you need to connect a large copper plane to LX pin to help thermal dissipation. and then you also need to keep sensitive signal traces such as feedback traits far away from the honest grain. If you follow all these rules, you'll get a good design under the gun.
All right.
That's a crash course. I don't know if you want to continue on this or not.
I think that we've covered everything technically, right? Like,
Yeah.
just sounds like
Generation. And actually, the nice thing in the other data sheet was it gives you an example of a bomb that would actually be something that a manufacturer would need. Where was that table?
like TI sounds like a great resource. I'm surprised how much math and manual stuff is needed to actually implement any of these.
Yeah. It's not as like cut and dry as just like being able to auto generate anything these days. I mean, I feel like it should be, but we're still getting.
Yeah, I mean I think that's what Flux promises, right? The Flux CDA.
Exactly. I think that's what they're promising. I also think that Altium has some like Altium's the SolidWorks of PCB design. I would say they're kind of like the professional.
Right. Altium. I remember that
They
name.
must have some add-ons nowadays. I'm just a big proponent of the open source stuff. But so if you take a look at here, just real quick, this is an exact bill of materials that you could send to a manufacturer for doing the pick and place for you. So you will essentially all bomb generation tools will give you lumped references if you're using the same part for each one of those capacitors. So like C1, C2, and C14 are all this capacitor. It is a description, some sort of capacitor, ceramic. Capacitors have a couple of parameters. So one is the voltage rating, one is the actual capacitance, and something called this X7R is kind of, you can think about it as a thermal rating. So there's X5R, X7R, COG, NOG. Like all of these things mean they're like standards for how capacitors can be made to resist temperature or like have tighter tolerances even with higher temperature ranges.
Okay.
Typically, if you need a really low noise capacitor, you will use like higher values in this X7R. So like X7R is lower noise than X5R. So you can, or tighter tolerance in capacitance and like how it handles higher frequencies and all that. And then you need the manufacturer number and the quantity. And this is the footprint size, right? The 0805, 0603, 442, 812, and you, with the reference, the manufacturer part number, description, footprint, another like value field, I guess, quantity and manufacturer name.
How do you figure out if you need X7R or X5R or one of the others?
They will tell you in the data sheet. So certain capacitors, so for example, if we go out to C out, right, so the output capacitors smooth the inductor ripple and provide a source of charge for transient loading conditions. You want ceramic capacitors to provide very low equivalent series resistance. So this, capacitor ideally is just a pure capacitor, but in reality, you can model a real capacitor with an equivalent resistor that's in series, so you're getting some power loss in that capacitor as well.
Right.
So this will sometimes tell you choose an X7R. Actually, here you go. So the C ramp, the ramp capacitor, which is used for necessary for the emulation ramp circuit. So this is part of like how the control system works in this particular IC. They have an equation for it, and then they say a COG type capacitor with 5% or better tolerance is recommended. So again, the data sheet will just say use X7R, X5R, COG, all that kind of stuff.
Okay.
And you kind of want to follow it. And again, the design example, where's that? Will tell you, right? So like because a lot of these will be the exact same, so all of the filtering capacitors will not change whether you're using like 5-volt output or 7-volt output. Like by filtering, I mean for the VN pin, like all those small capacitors that we saw on the VN side, those will generally not change between designs. So you can just take a look at this and say, okay, they're using X7R 25-volt 1 microfarad capacitor. That's what I'm going to need as well.
Right.
And then there's like patterns, right? Like you will typically see patterns like, hey, I need a bigger size capacitor for this part of the circuit, always like the feedback part, because it always ends up being slightly higher thermal like location. So they're allowing a slightly bigger capacitor because that will help not overwhelm the capacitor with thermal. It won't soak the capacitor with a smaller volume with the same thermal like resistivity and all that kind of stuff. So it's one of those things where it's like once you start seeing the patterns, it's kind of like, okay, cool. I just know I'm going to use an 0805 or an 0603 for this particular purpose circuit.
Yeah, makes sense. What else?
One last thing maybe we could go over is the file for pick and place. So
Oh, yes.
right now we have these footprints, but nobody can, and let's say we have the BOM. So like the manufacturer knows what components you want to use, and they also know what the PCB now looks like. In order for you to generate how the pick and place machine needs to actually grab the component and then place it in a certain orientation and a position, you go to fabrication outputs and generate component placement file. Now, there are also sometimes manufacturers will say that they prefer that the drill file that we used or that we generated before, we use the origin for that, or we can just use the global origin of the file. Typically, what I end up doing is I always set a manual drill file origin. So if you go under place and then reset drill origin, I'll just choose one of the corners of the board. Let me be on there. Why is it not letting me do that? Oh, that's reset. Sorry, place. You need to do drill/place file origin, and then KiCAD has some snapping features, so you'll typically
Nice.
snap
Yeah. I was gonna say like you were just eyeing that out, but yeah.
No, yeah, it'll snap. It wasn't snapping because that wasn't meant to be. But once that's done, everything will be referred to with respect to this position. So we actually generated that component placement file, which we will do. It's very quick. It's just a CSV file.
Oh, interesting. It's just coordinates. Yeah, okay. It's very simple actually.
Right, so it's got a reference. It's got the value should be like 10 ohms, 10 kilo ohms, whatever. This is just R because in our schematic it's still R. The package shows exactly what kind of footprint we're using. It's an 0805. So 0805 is the imperial version of the thing. 2012 is the metric. So like those are the same thing. So 2012 M and 0805 is the same footprint, they're just different standards. And then it's got position X, position Y, and then minus 90-degree orientation, and then what side of the board is on. So if you have placement on both sides of the board, then you'll have like top and bottom. But in this case, we only have components on the top side. So maybe I should show you something else there is if you do need to flip a component to the bottom side, like place a footprint on the bottom side, you can just go there and then change the flip sides. Right, so now this is actually on the bottom side
of the board. Okay, got it.
So if we take a look at the 3D view again, you'll see that R1, R2, and the chip is on the actual bottom side.
But they're still connected, right? So it goes through the board somehow.
No, they're not connected. So you can see how we have this line now showing that we're not connected to the pin. And it's not only just because the pin has switched sides, because it's kind of flipped or mirrored, it's because this trace does not go to that back board. And the way you do that is by creating a via. This is essentially a tunnel through the board in the Z axis. So if I create a via there, and then I connect, the other front layer, if I connect this guy, so I want to select, and then do it this way. That is really annoying. All right, hold on. So I can connect it to this via.
Nope.
Every time I try doing something nice, So I deleted the via. Typically, the way I do this is I actually trace it out to where I need it to go, and then I press V, and then I'll create the via with the
Oh,
thing, and now I'm on the bottom side.
nice.
So this, by the way, is going through all of the layers. It goes through front copper, in one, in two, and then back, and it goes out the back.
How does it know which layer to go to?
Well, for components, they're always going to be on the front or the back layer, right? You can't put a component. So, with respect to what you might have in the middle layers, we might actually, for example, typically on all these designs, you'll have one big copper fill for a ground plane, and we'll show that next. Essentially, let's say you want the whole board to be a copper fill. I typically just create a rectangle of the size of the fill that I want. So this is, because it's green, by the way, I'm in my in one copper layer. Let's say this is the rectangle that is going to be my copper fill. Once I have the rectangle doesn't define anything, it's just a shape, but I can use the copper fill zone tool, which for some reason doesn't do shapes. You have to like outline it yourself. But essentially I can say that this is going to be a ground copper fill. It's going to be only in the in1 copper layer. And I'm going to use the static tools to help do that. So that is now the copper fill. I'm going to delete the rectangle, but you can see that this is an unfilled copper area. So when I go to fill it, this is Shift E I use, but you can also, I think, there's a thing somewhere that does it, but essentially this is now a filled copper area in my first layer below the front layer. So if I go back to the front layer, you can see my components here. If I go to the back layer, it'll like highlight different components based on what layer you're on. And what you can see is this hole right here is because I have a rule that says I need to be 0.5 millimeters away from any vias that are not
I see.
that are not the exact same type of the net main here that I am. So because this is a ground and this is not a ground trace, it will create that hole automatically for you.
Got it.
And then that's the same thing for, like, for example, if I put another layer on the top layer, so if I did let's do the back layer because it's more interesting. For whatever reason, this is something you typically wouldn't do, but like, let's say you put a full copper layer of a power plane. And that's not true. You actually do, if you take a look at your Arduino, one side will have you'll actually be able to see this. The top layer will have a plane that's like surrounding all of your components. That's probably the ground layer, and then the bottom side will have another one. Or that bottom layer could be ground or positive 5 volts, because it's easier to just be able to tap into those 5 and ground or 5 volts on the ground in different places without having to trace anything. I'll show you what it looks like on the screen.
Actually, yeah, I see the ground. Well, actually, no, I see the 5 bolts.
Yeah. You'll
The
be able
ground
to
is
start
probably on top.
recognizing what looks like a copper plane and what doesn't, or what's a trace and what's not a copper plane. We'll actually visualize it in Visual Ground in a second here.
Yeah, I don't think I can see the ground on these boards, but I definitely see the voltage.
So let's say, just real quick, I'll show you, for example, if I wanted to make another copper plane that's a plus or positive voltage, I just say 22 volts nominal. That's what this copper plane on the back layer will be. I'll create a rectangle. I can delete the rectangle, and then I'm not, like, it doesn't matter what layer I'm on. If I do the fill all copper zones, it will fill every single copper zone. And you can actually see what happened here is that because this chip is actually on that layer as well, obviously the plane can't go through the pads that are not part of the ground, right? So, and we haven't connected any of these other, these other pins to ground. So it doesn't connect any of them, and it actually creates an outline. So if I grab this plane, you'll see that there's an actual outline for that chip. And the other thing we can do real quick, just to you how this would work in a nicely automated way.
Wait, is the chip on the copper layer? Why would that? Yeah, it is, right?
Yeah,
Oh,
because
okay, I see.
you can have copper layers on the same layer
I see.
as pairs, on the
Yeah.
front of that pair essentially. But the copper fill needs to not fill in those places because otherwise electrical will be connecting anything.
Right. Yeah.
So let's say I connect my EP to ground. EP again is this big pad in the middle, which is definitely going to connect to ground. I can, so even though I saved it in the schematic, I still have to pull it in here, and then you have some options here for like what you want to actually pull in.
Yeah.
But I typically just do all of them. And then as soon as you do that, you can see how the first thing that happened, right, is that this has now gotten the same ground value as this resistor here.
Yeah.
So the resistor is telling me that I am not connected to this ground because these two, like ground is the same on the board, right? It's like one
Yeah.
ground. So if I go back and I fill in the copper zone again, and that doesn't work because that bottom plane is the positive plane, but let's say I switch that to a ground plane on the bottom. If I fill that in again, you'll see that it has actually now run over this pad, which means that those two things are electrically connected. The reason it's not like a full fill either is because you have options of how those things are filled. If you go back to the copper zone properties, pad connections right now are being made via thermal reliefs. So you're not making an entire solid connection, which would be a really big thermal sink. You're just making it very specifically thermal relief on two sides so that you're evacuating the heat very specifically through a certain side. This might be important for some components. For this, it's actually better to just do a solid fill because you want this entire pad to be connected directly to the ground plane. And so now you see that that plane has completely gone over. Now, the nice thing about having ground planes is if I need to connect anything, especially capacitors. So a capacitor, you know, like for example, the V in pin, which is pin 1, we know that there's going to be a capacitor here. I don't want to have to trace my capacitor's ground all the way down here because that still creates a bigger impedance loop, right? It still creates like that extra antenna area, so to speak. So what you do there is you literally create a via, and it'll automatically look at the planes below you, and it'll pick the ground plane because that's both of the planes that we have right now are ground planes. And then I can just connect this with via, and now everything is connected to each other. So this ground here is connected to this ground via this big ground. And that's typically how you do a lot of these, like, how do I
Interesting.
Like there needs to be a nice big ground area. Everything will have low impedance paths straight to the ground so that we're not like making big traces all over.
I see. Interesting. Wait, and this giant copper layer doesn't generate any impedance?
It's lower impedance, right? Because so impedance is resistance. You can kind of think about it that way. So the tighter your copper area is, the more impedance that actually goes through, depending on how much current you're trying to go through.
This is a huge copper area.
What's that?
This is a huge copper area, right?
Yes, but the actual, so if you imagine what would actually happen electrically here, the electrons would not go out to this edge.
Right, just the shortest path. Yeah.
Electron density, like if you have multiple electrons that are very close by, going through like a very narrow copper channel, let's say, like a trace, that is going to end up being higher impedance because you're shoving more current through the same.
Okay.
So to speak.
Yeah.
Whereas in this case, you have a massive surface area, and the density for electrons, two electrons end up in the same place. They have more space to move across each other.
Yeah. Okay, I could see that.
Yeah. And that's all you need to know, really. Like that's PCB design. Like the rest of it is literally me going back, checking the circuit, getting all the components in, and then laying it out exactly as the data sheet would show, and then tweaking it for like components we want to add. For example, if we want to put a microcontroller on here, maybe I put that on the bottom side and like create a little logical area so that I kind of isolate that from like where all the switching is happening, and then that will connect to a voltage sense or something along those lines.
It sounds like there's probably a lot of good practices to follow and stuff like that.
Unfortunately, a lot of this comes down to rules of thumb. I don't like rules of thumb It's just that in order for you to have any reasonable time for completing these things, you kind of just have to trust that the data sheet is telling you the accurate information. Whereas a more principled approach really would be go to a simulator, simulate your buck converter design, then take the parameters that you're seeing from the data sheet, like that are based on test data, put those into your simulation parameters, and then fine tune until you get a final set of components. But that is just an obscene amount of optimization, and you just have to trust that TI or Analog Devices or FPS have done that optimization.
Okay.
Realistically, they probably have because they want the best product, right?
Right. What else should we cover?
I think that's it. Like realistically, you could go and design a PCB now on your own.
Yeah, I think a power PCB for something like this is probably not the first PCB you want to design.
No, I think if you want practice, what you should do is design. So that that power distribution PCB that we're talking about, not the power supply PCB, but the one that just distributes like to the different. It takes in as an input our 7 volts, and it takes in as an input like the PWM signals, the different ones.
Yeah.
And use those two things to one output. That would be a PCB that's very simple to do. You're just kind of combining inputs into one output.
I can try that. Yeah, right? Because it's just copper routing, right? It's probably like one layer.
No, you'd still want 4 layers, right? Because you are going to want. You could maybe get away with 2 layers, just increase the copper density, or like go from 1 ounce to 2 ounce, because we are still passing all of that power for all of the motors through one PCB at that point, right? So like that big trace that comes, like that big copper area that we first connect to for, like, let's say the output of this board connects to that board. There's gonna be some beefy wire, and then that trace on that board, or that copper area that accesses that, will have to accommodate all of the current. And then as you split off into different channels for specific servos, that's when like the areas go down.
Okay, maybe I'll do that one.
Yeah, I mean, I would focus on getting the like what you have, basically working with the Arduinos and all that kind of stuff. I think we can maybe do another session where we can, work on that one together, or do like a little bit of a pair programming thing if you want. This one I think is just going to take me some time of like putting on my headphones and just cranking it out. But
how much do you think it will take to finish board 1?
This one?
Yeah.
How long will it take? It will depend on some of the other stuff I want. Like, what should I prioritize? Should I prioritize the training and getting the model of this?
Oh, I wouldn't prioritize this board. We're good. Like, yeah.
The only reason I would prioritize this board is because I want somebody else to assemble it. So, like, if some of these components take time for JLC to get,
I see.
I know the schematic and like what components I'm using, I can buy the components so that JLC starts getting them in. And while JLC is getting some of those components, I can finish out the layout and then get them to produce it. So like I'll try to make that parallel just so that we can get one of these boards in our hands. Because then we'll, again, if something is wrong, then we'll have to re-rev it and update the design and make sure that it works. But I do think that we'll be able to get a very compact solution with this. As you can see, even with this one, the switches that we're going to use are not too much bigger than this, and the inductor is going to be about the same size. So, like, the buck converter 1 could be this size, and because buck converter 2 is very low power, you can probably fit it in like a very small sliver, just depending on how you can lay out. Right?
Okay.
And again, if you put this control chip on the backside, then you get even more real estate.
Right. Which we should do, right?
We should do, right. Yeah, it's just slightly more expensive for the assembly side, because now you have 2 sides to assemble.
Right. But no, we need the smaller footprint, more density.
Yeah, which I definitely think we can fit. Like, we can fit 2 buck converters on this for sure.
But just for reference, this is probably what, like 4 hours of work?
Yeah, this would be. Yeah, I think I could get this done in 4 hours of work.
Okay. Yeah. Yeah, but like I said, like I wouldn't like I'm good to go like without this board right now. It's just as the package gets cleaner, it is very important, right? Because like yeah, these cables, like sure, I have a new packaging that's gonna make it look neater, but there's still a ton of cables, right? So yeah,
Yeah, I mean, you're never going to get rid of the wires to the motors themselves.
yeah,
It's just going
exactly.
to need to retain them in a nicely zip tied way, and then also
Yeah,
connect it all to like one central location or something like that.
yeah, and I also really want to make that robot slimmer, man. Like it's
Yeah. When I think, I don't know if you've taken a look at the system diagram, but this is like what I thought was an overall, like if you actually wanted to deploy a robot to somewhere remote, then you probably need all three subsystems, and you can kind of see how you can kind of clean up your. You'll still need certain connections between all these components, just because you need to run communications and power to both of those, like both power and communication to all of these things. But you can clean it up quite a bit if you make them modular. Like each leg has a small PCB that can distribute the wires for just the leg, right? Rather than having one central PCB here that does all of that. So we might actually want to think about doing a smaller distribution PCB
I
somehow
see.
that is more modular, and that takes a little bit of like, okay, how much space do we have?
Because we have, I guess like each leg right now has technically has 9 wires, right? And we could bring it down to 3, right? Ground power and some sort of I2C communication,
Right.
I guess.
So you could say you could do something like in this diagram you can kind of see what would happen, right? So like you could send all of the power you need using one big cable. Let's say you have a cable with 2 wires that are like internal, whether it's just like zip tied wires together or like an actual cable with 2 internal wires. You can do that and then plug it into your left leg module, which would have a small board that would essentially take the power, distribute it, and then another line for the communication would come from the computer to that leg as well. Or you could integrate all those into like one cable, right? Like you just have like bus minus or bus ground and I2C or PWM, zip tie all those together and then just route them to that leg, and each leg gets the same cable for that like
Yeah,
cables.
yeah, that would be cleaner for sure. But we should definitely drive towards those kind of
Yeah.
cleaner out. Like, I think all these things will add up, and we'll have a very compact package. By the way,
Yes.
I think it's not I2C. I think it's I square C.
You say whichever one you want to say.
Okay.
I've heard people say I squared C. I call it I2C. I think both of those are acceptable.
I've
But
always
yeah,
said I2C, but I just remember someone once told me like it was I square C. Okay.
yeah. No, I think both are acceptable.
Cool. Yeah, let me see how much progress I make next week, and maybe we can do another call for board number 2. I mean,
We can definitely do a design review. So like once this board is done, let's get on a call and we can like go over every aspect that I've considered for the
cool,
schematic.
cool. Let's do that.
We can review of how the board came out.
Yeah, let's do that. The other thing I was gonna do was I was looking into Mojuko just to like try to run my own simulations for the controller.
Yeah.
I was trying to figure out if what would be easier. Should I just buy a GPU or should I figure out how to run it on a GPU in the cloud? Did you ever look into cloud hosting the simulations?
Yep. Actually, we need to get on a call with Ignacio because he has this work. Like he has just been running simulations in the cloud. That's the only way he's been running.
Oh, perfect.
So we already have somewhere in our repo the ability to do this.
Cool, cool.
So I'm actually meeting with Ignacio on Sunday at 2:30. If you're free, I'll just add you to it. But if you're not, then
No, I'm gonna be in Yosemite this weekend. Yeah,
nice. Okay.
but let me know what comes out.
I think next week at some point we should just get on a call all together. I don't know when that would be.
Yeah, I have a lot of time right now.
Yeah. That's fair.
Yeah.
And then I'm going to be in Boston November 4th to 8th for work, so that might be a busy week for me. But before that, I'll be pretty open to continue working on a lot of this stuff. So I'm going to try to make a lot of progress on the getting like this exact model. What I'm trying to do is get a simulation of exactly just this model and like have the motor just turn from here to here with some sort of mass that I know.
Nice.
And once I can get it to replicate that pretty accurately, I know what parameters we need to put in simulation for this motor.
Nice, nice.
Another problem that I'm running into is though, you know, Onshape can generate your inertia matrix for like all the different components. Like, can it generate one for like this little thing and then?
Okay, I've never heard anyone call it an inertia matrix. It can definitely do that.
What's it called? What do you call it?
Oh, dude, just inertia component. The inertia parameters for each component. I mean, Onshape can try, right? Onshape doesn't know the infill settings. Like, it's gonna be slightly.
Well, yeah. So if we assign like a material that's plastic for the infill settings, I think you just have to erase the mass by, because the inertia would stay the same, given that your infill pattern is regular, so like it's uniform density.
But who knows?
That would just be erased.
But who knows what the infill pattern? Because the infill pattern depends on how you put the parts on the bed.
Maybe I'll just go 100% infill.
No, we can just probably estimate. I think we'll be close enough.
Yeah, but I do need the inertia matrix.
So what does that mean? Inertia for every part on all axes of rotation that they have?
I need the 3x3 inertia matrix. So the diagonals are your major components, and then your offset components, so like I, X, Y, I, X, Z. Those are usually 0. If those are 0, like, and we can estimate those as being 0, then I think it's fine. But once I put a step model into the Mujoko model file, I need to also define its inertia.
Man, I'll be very surprised if Onshape can't do this. Like, Onshape disappoints me in a lot of ways, but this would be like a new peak of disappointment, you know?
Yeah.
Yeah, sure. Material has not been defined. Hold on, I can fix that. Sick. Actually,
you can teach me some of these mechanical principles too at some point, because I'm like kind of out of the loop on college.
wait, what's the principle here? I'm just clicking around.
No, for like fitting parts or like what college said. This is something that I need.
Man, I've been suffering with Onshape. It's been bad. Actually, I have no clue how to set a material here, but well, okay, so how to set a material on Onshape. Library, first drop down. Select the library tab. There's a library tab? I do not see library tab. I see. I've been lied to. I know, where would you put your materials if you were Onshape? That's usually what I ask myself.
I didn't do the Onshape model like a day ago when I think I like blew up the assembly somehow, and I quickly control Z and closed the model so that I wouldn't mess everything up.
Man, this is okay. What if it's out here somewhere? No.
Here, hold on. I can try looking it up.
Oh, I mean, it said select the materials tab, but part. Oh, okay. Oh, I got it. So, man, it's so easy. Onshape is very. Oh wait. Oh yeah, assign material. Okay, materials. Okay, PLA.
Yeah.
There's no PLA.
PLA is acrylic, right?
Oh, is it? 1.25.
Oh no, sorry. Poly.
Oh, in kilograms millimeter cube.
You can do
1.25. No, grams, but oh my God. I mean, it's gonna.
It's gonna be.
Oh, dude, PLA, easy.
Yeah, that makes sense. G and PLA should be pretty similar.
Anyways, this assumes 100% infill, right? So.
Yeah, that's fine. Let's just see what it comes out. What's the mass? Like, it should tell you the mass too, right?
Yeah, the mass is 50 grams.
So I think the way you do this is you essentially take the mass of what you had here, and then when you slice it, and Rue printer tells you what the mass is, you can use that to derate the inertia as well. Okay, yeah, so that's perfect. That's the matrix that I need, right? So it's got the that also depends on
Their axis of rotation.
Support this matrix because those values actually depend on which orientation, like in your model, it is. Right?
Yeah, isn't this? It depends on the axis of rotation, no?
Yeah, it does.
So you should be able to select an axis of rotation.
Yeah.
I mean, now we might be asking for too much, you know, show analysis tools. I mean, I know SolidWorks can do it, so it's like, don't tell me you can't do it.
Tool we can use to do it too. Like I know Blender has add-ons that can do it too.
Yeah, this is really sad. It might not be possible.
It must be assuming that the inertia is based on some sort of coordinate, right?
Yeah, the CG, right?
Yeah.
Yeah, it might be just easier to export this somewhere else.
Yeah, okay. That's fine. I'll take a look. I'm pretty sure Blender can do it. So as long as I can get step files for all these things, I can, or even.
Yeah. This is the cleanest the CAD assembly has ever been. Like, everything works, nothing's broken.
Yeah, it's pretty clean to me.
It's for the first time. Things are clean.
How do you decide, like, how does that, like, are you just rotating it visually, or is it actually made it and it only allows you to rotate one way?
No, it's visually. Yeah, so there's like no surfaces that tell you, you know, there's no good hard stops or anything. It's all visual, which is something that needs to be improved.
Yeah.
But the legs have not been improved. Everything else has been improved, not the legs. So yeah.
Well, what did you say about the legs breaking? Was it?
It was this joint here that it was breaking, but it's been fixed since. It hasn't broken since. Now it's the electrical stuff breaking, but yeah, it shouldn't break anymore. Yeah, everything feels pretty solid. I also, I don't know if you saw, but yeah, basically it fell. Basically the legs were very jerky. I don't know if I told you, it's like one of the rear legs kept moving around, and I thought it was because Arduino is quote unquote noisy or anything. But it's actually because like I had the PWM for the rear shoulder connected to pin number 1 in Arduino, and pin number 1 is the same pin used for the serial console. So when you initialize the serial console, it basically sends a bunch of stuff to your servo, and it starts jerking around. And so basically, you can switch pins, but I just don't initialize the console anymore because I don't need it. And yeah, it's been fine since.
Yeah. Okay. Cool. So
but
I mean,
in
that case, it seems like the Arena is perfectly fine with driving this. It's just more about like getting the power to these.
Yeah. Yeah, and the other thing I did was I bought some joysticks. So I'm gonna try to do an analog control joystick to like drive, and that's my goal for next week, to get this to actually take a step, because it can stand, it just doesn't walk. And it's like
very unbalanced. I assume that's because it's got a pretty high center of mass, whereas like if it's on two legs, then obviously you're gonna like tip diagonally, right?
Yeah. Also, the legs are not perfect, like. Because like when you assemble these, it's like, oh, how do you know which angle to put the leg in? There's no clear way. Because I should have a tool or a surface to reference things off. I don't, so I just eye it out. So it's not perfectly even, all the legs. So I could have some software trims.
Yeah, can you build in some sort of like keying feature in 3D print itself?
Yeah, I should. Yeah, it's just I haven't touched the legs in a while. But yeah, I definitely should. Yeah, it's just I was trying to walk before like spending even more time on CAD.
Yeah, that makes sense.
And like
I
the other
think,
thing is like I actually don't know how to walk because like I can kind of like I guess I can hard code a step, and that's one way of doing it. But then it's like, oh, I guess you need like a walking function and like, you know, different legs. How do you decide where to walk? And like, oh, what if you want to walk? What do you want to stop mid step and things like that? I haven't thought through any of that.
yeah. Let me see if I can find something. 'Cause
I mean, I already talked to ChatGPT about this, and it's like I think I understand what to do, but it's just it doesn't feel.
I think what you have to do, this is definitely there must be like an analytical solution that's very already like well implemented out there where you can say like, okay, I have my legs of this size, each joint is this size, and I want to be able to walk forward. So like one moves a little bit, like two moves a little bit, and then there's like a sequence. It's just cyclical, right?
Yeah, that's a good way of putting it. That's not what I was looking for, but yeah, right. I should not be having to hard code stuff. I think.
Yes, I agree. It might be easier to hard code things just to get it to walk a little bit, and then
Yeah. That's the first step for sure. Like that's what I'm doing Monday, Tuesday. I'll be surprised if I don't get it to walk by Tuesday or Wednesday. Yeah.
Yeah, and then the other thing that I still need to figure out that's gonna probably take a little bit of time is I need to get the Raspberry Pi set up so I can start simulating the neural networks on there. But really, the end goal here is, let's say the mechanical and the electrical work out pretty well. I think that is pretty easy long term. Like we're gonna get there.
Yeah.
It's not an uncertainty really. The difficult part is it's going to be how do we take the neural network, which is admittedly very small for the motion controller, and get it onto the Raspberry Pi. I don't think that's that difficult. I think there might be some conversions we need to make, so like from the JAX format to the Onyx format or something along those lines. And then from there, as long as so like the simulation or the neural network outputs might be like between zeros and ones, right? Because like that's what its output might be.
Yeah.
Go from position 0 to 100% your maximum because of position-based control. Then we'll have to use some sort of thing to convert that 0 to 1 to like an actual message that gets sent to each servo driver.
Oh yeah, true.
And then that would have to convert it to PWM, which is that is just maybe that chip that we use or something like that. But there's still like a bunch of infrastructure stuff that needs to be completed.
I mean that's just software, I think, right? That's just code.
Mostly software. There might be weird things that show up with like, oh, I2C speed fucking.
Yeah, it'll be cool. I really need to go eat lunch. I'm like passing out.
Yeah, I have to go eat dinner. It's 8 for me, so.
Oh man, it's 5 here.
I think it's cool. Thanks for this. Actually, talking through some of this design work helps me frame out in my mind what I need to do as well. So it really does.
Yeah.
Solidify that.
Yeah. I guess the issue with like talking through everything you're doing is that it does. I feel like it makes you slower, or at least I feel like it makes me slower.
Dude, I would have, like way slower.
Yeah.
You're trying to get all of the stuff that you're thinking about into words that make sense. Which is,
exactly. Like it's like I don't want to say anything too dumb, and it's like I'm just like okay, and whenever I get blocked on something, I'm like, oh well. I mean, it's like you're recording it, and it's like you better come up with a solution fast. Yeah. So.
All right.
Yeah, let me know what comes out of what Ignacio says, and I will send you footage once we're walking.
That's gonna be so cool. It's gonna be so cool.
So we just wrapped up that call with Manit. Again, I think he's a really smart guy. He's a friend. We've been friends for a long time. Like we mentioned, we work at Tesla, and he's done a lot of cool stuff. He actually works in robotics now. Like he's a professional robotics engineer. And he has that background in electrical engineering. So I hope you enjoy that crash course on how to build a power PCB. I have never designed a PCB. Have never built a PCB before. I've obviously done electrical work. I can wire things. I've done breadboards, stuff like that, but never designed a PCB. And sounds like that power PCB is kind of complicated, so I wouldn't want to start there. Manit's gonna do that. You know, he obviously knows what he's doing. I might help out with a simpler PCB. I do want to like try something for the first time because, you know, I think it's really good to be able to have, you know, these friends and experts to help you build things, but it's really important to be able to do everything on your own if you know, if possible. That way you can always provide feedback to others on their work and stuff like that, and find room for improvement on the robot in a holistic approach that takes into account all systems, not just mechanical, not just electrical, not just software, but the whole package. You also mentioned us talked about this other guy called Ignacio. Ignacio, it's more on the software side, on the machine learning side. We haven't involved him too much in the project. Hopefully, you know, I can convince him to spend some more time helping us teach this dog how to walk using an ML controller. We'll see. We might have a call in the future. For now on, I'll just, you know, I'll keep on building. I'll keep on making these videos. Next video, you know, like we've been talking, it's like we're gonna implement all those changes we've made, all the cleaner packaging. We're still waiting on 3D filament and new wires and new electrical ports, but we're gonna get this robot really solid, and then we're gonna teach it how to walk first with analog controllers and eventually move on to something better. But thanks a ton for watching, and let me know if this was let me know if you learned something, or at least if this was entertaining.